So now welcome to local area networks, wireless communication. So why the emphasis on this big system and this local system? Because this is so typical that depending on the application, you say, well, if I'm driving across the country, then I need one of these bigger networks. If I'm within buildings, I only need a local network. Why can't I use one technology for the other? Well, after this chapter, you will better understand why. One of the reasons is those systems have never been designed for this. So if you take one of these big systems for very local use, there's not the capacity, and they are way too complex to operate those systems on your own. So if you try to operate your own BTS, your own eNode B, that's way too complicated. So it's much easier to set up your wireless LAN router. On the other side, if you try to use wireless LAN to cover a whole country, I know there are some of these proposals, those technologies have never been made for this. So, not very good management interfaces, not very good coverage, what do you do about frequencies, etc. So, the data rates will completely break down, that's one thing, plus the energy you need. So there are some calculations, for example, to cover a whole Germany with wireless LANs needs 2 new nuclear power plants. So we already waste a lot of energy for these wireless technologies, but to use wireless LANs for a whole country, that's not really a good idea. The medium access mechanisms are never made for longer distances between your laptop and the access point. So after this chapter, you will understand those wireless local area networks can really not be used to cover longer distances. Yes, I know there are experiments. Oh, I use wireless LANs to cover 60 kilometers. Point to point, no problem. Well, it's electromagnetic waves. It's the same nature, same physics. Yes, you can cover 100 kilometers with it, point to point. But try to set up a network with medium access, with all these distributed systems using wireless LANs, you're lost, completely lost. And usually the wireless LANs, 20 meters, 30 meters, 50 meters, but then after 50 meters, they do not really work in a normal setting. Yes, you can receive the signals after 100 meters, 150 meters, but normal setting means dozens of users, normal traffic, many other networks. So for example, in my home I receive 46 wireless LANs from all the neighbors. Okay, so you better escape to frequencies the others do not use. So 5 gigahertz, for example. I will explain this later on. So wireless LANs have never been built for the coverage of larger regions. And also it's difficult to use these more complex, huge systems like LTE. You can do it, but it's more difficult to use them for, equipping a building. There are femtocells, there are picocells. You can extend the LTE technology into buildings. Yes, this all works, but to operate those systems, because the wireless LANs are operated by you, that's one of the big differences, compared to we only have 3 network operators for those big networks I explained in the last chapter. So now, wireless LANs. Yeah?
There is those people who want to build wireless LANs everywhere. Could they also use LTE technology, or is this proprietary somehow?
No, so the question is, can we use LTE technology, basically LTE, to set up local wireless LANs? Yes. The answer is really yes. Yes, you could do this. Yeah. So, because in the end it's a different radio access, but if you look at the technology needed behind all this, if you want to support mobility management and this, then it gets more and more complex. If you stay with this, okay, radio access, in theory, yes, you could do this. And indeed, you can set up your own LTE cell at home. Yeah.
But wouldn't they need the frequency?
That's a different story. That's a different story. You didn't ask if it's allowed to. You only ask if it's possible. Yes, it's possible. It's not allowed.
Yeah, but is it possible to build it in the frequencies of the wireless LAN?
Yes. So the question is, can we build LTE in the frequencies of wireless LAN? Yes. Yes. I'm not aware of devices doing this, but if you stay within the limits that is regulated in the wireless LAN, I will come back to this later, there are certain limits, but in the frequencies for the wireless LAN, and that's in contrast to the other frequencies we use for GSM and LTE, the regulation does not say which technology to use. So you could operate your whatever the technology as long as you stay within the limits, like maximum output power, for example. So there are some limitations in output power. And the same is true for example, 868 megahertz. You can use whatever technology, but maximum output power, maximum duty cycles. So there are some limits. So indeed, at 2.4 gigahertz, there are different technologies. Most prominent, wireless LAN, following 802.11, that's one, and Bluetooth, following 802.15. Two different technologies, complete different medium access, but both at the same frequency. Plus, most of you at home have another device with a big, huge output power operating in the same frequency, microwave oven. Your normal microwave oven operates at exactly the same frequency, 2.45 gigahertz. That's exactly the same. Hopefully shielded. Otherwise, yeah.
Last question, but wouldn't the telephones or the mobile phones, or aren't they by hardware specified on searching for LTE frequencies on a certain...
Yeah, that's a different question. So your normal mobile phone, you cannot operate at 2.4 gigahertz. It would never search there because there are no LTE channels defined there. But in theory, yes, you could do it. And if you know how to build your own equipment, yes, you could do it. And it would be even legal if you stay within certain limits. But there's no device doing this. No, I'm not aware. But you could.
Sorry, maybe another question about the big networks. Could you explain in short how the Deutschland network fits into all this? Because I need a completely different router if I'm a customer of Kabel Deutschland. So what are they exactly? What kind of network?
So the question is, what is special about network operators like cable network operators when they also offer wireless services? I guess that is the point, because
what generation network do they have?
So basically what they do is nothing special. The routers the cable network operators use are cable modems on one side, on the other they offer wireless LAN. It's a normal wireless LAN technology following 802.11, and the only difference is they set up a kind of a virtual network on top of this that all customers of the cable network can use any of these modems. And the same happens with other operators, so you can easily set on top of this hardware infrastructure kind of a virtual network offering these hotspots to other customers. But there's no special fancy technology. So it's a normal cable modem, so a modem that has, well, for cable networks on one side and wireless LAN on the other side. And other routers are DSL routers, DSL on one side, wireless LAN on the other side. Nothing special about this. And then, on top of this, you set up a virtual network, special pricing models and whatever, but that's independent of the technology. But normal routers, nothing special. Okay, you already see by looking at this very short outline, so we'll focus on 802.11, the wireless LAN technology. If you follow to the end, you see, oh, that's not a single standard, it's 11. Oh, it was A, B, G, A, C, A, Y, A, O. That's complicated. Why? Well, these are the kind of evolutionary steps towards faster and faster technology. Today's devices, they usually are able to follow this AC. Typically AC standard, offering we will see several hundred megabit per second AC, but there are some more standards, higher data rates and different other things. Okay, so I will touch wireless LANs, I will touch Bluetooth, and then very briefly some other of these standards. These are all wireless standards. I will not go into details. on these. There are some metropolitan area network, etc. There are some other wireless technologies, also not the main focus here. Okay. To make it a little bit clearer, I know this is not really complicated, but it might be confusing. When we talk about wireless LANs, we typically talk about the family of 802.11 standards. 802 is the standardization body of IEEE. They also standardize Ethernet, 802.3, for example, that's Ethernet. 11 is wireless LANs. And after development of the first initial standards, we had new technologies, etc. And they came up with 11A, 11H, 11B, 11G. And A went to 5 gigahertz, B and G to 2.4 gigahertz. So we have technologies at 2 different frequencies. Those frequencies are the so-called ISM bands. ISM stands for Industrial, Scientific and Medical. So if you see normal medical devices operating with microwaves, they operate at 2.4 gigahertz, for example. Your microwave oven at home, 2.4 gigahertz. Many other devices operate at 2.4 gigahertz. And there's also the 5 gigahertz frequency band. So the 2.4, these are license-free frequency bands, so you do not have to buy a license to operate your device there. On the other frequencies, you or your network operator has to buy a license. You remember UMTS, 50 billion euros. That was the cost for the licenses. Here, this is a license-free band, so everyone can operate without paying any fees the device on these frequencies. And there's 5 gigahertz, which is a license exempt band, so you don't need a license, but there are a little bit different regulations because there we also have flight radar. So there are some radar systems at 5 gigahertz, and if those devices at home detect interference with radar, they have to avoid these channels. And depending on your DSL routers, look it up, go on the page of your wireless LAN, go to 5 gigahertz, and you will find the entry detected radar. Sometimes it detects something, sometimes not. So it's interesting, and then your box has to avoid these channels to avoid interference. So a little bit different regulation, but in the end you can operate your device. And then there are many more standards, 802.11i, for example, security, etc., etc. More standards, and we will see more and more. To make all this interoperable, there's the so-called Wi-Fi Alliance. The Wi-Fi Alliance, Wireless Fidelity Alliance, is an industrial consortium that tries to harmonize services interoperability between the devices. Because even if you follow the standards, there might be some options, one vendor picks these, and some options, some vendors picks those, and then they are not 100% compatible. So we experience, for example, a dramatic breakdown of our data rates if someone of the students comes with older devices, old 11B devices, and the standard then says, oh, if you detect one of these devices, boom, you have to bring down the data rate for all the devices to the lower data rates to be backward compatible, etc., etc. So that's the Wi-Fi family, 802.11. That's exactly the base stations you see in many of these rooms. We have, as I said, 1,880, something like this, of these hotspots on the campus. Then there are these more personal networks built into many devices, wireless personal area networks, and most of them, they are based on the 802.15 family. There is the so-called ZigBee technology. ZigBee is again an industrial alliance, standardizing everything around home automation, home control systems using this. And there's Bluetooth more targeted towards cable replacement for headset and mobile phone, things like this, or attaching your camera with a printer. Spontaneous networks, set up a spontaneous network. That's the basic idea there. ZigBee has some other features, and you see how many standards there are already. 802.15 for A, B, C, D, QRS, whatever, wireless body area networks, and this and that. For you, it's not important to know all the detailed standards, just to show you there's a lot going on. If you're interested in these standards, look up the pages of IEEE. You will find all the information on the pages of IEEE. You will not find all the detailed standards there because IEEE lives from selling standards. It's one part of money they make. So you will get the standard typically half a year after publications. You will get them for free.
How does the process with the standard work? Like they set the standards and then the countries have to free the bandwidths for ZigBee, for example?
No. So the question is, how does the standardization, freeing bandwidth, etc. works? So first of all, there was the World Radio Conferences, etc., and they allocated different frequency bands for different purposes. So everyone knows since many years 2.4 gigahertz is available. And then standardization set in and said, oh, what can we do with these frequencies? We can do some stupid things or some more intelligent things. And then the standards evolve. No. So IEEE has nothing to do with the frequency allocation. They cannot say we want to use this and that frequency. No. It's just the case that if you have a brilliant technology but no more free frequencies, it could be the case that you say, okay, let's free some frequency for this technology, like what happens now, LTE at 700 megahertz. So there's the technology, new technology, LTE, and there's the frequencies around 700 megahertz used for older technologies. And then politics have to decide to free the frequency. That is exactly what happened a year ago when our minister responsible for internet, digital infrastructure, etc., decided we will use the 700 megahertz for LTE technology and we will sell them to whatever operators. So then this is a political decision.
So the standards are completely independent of the frequencies?
So basically the standards are more or less independent of the frequencies, more or less when it comes to the physical layer, because you need the frequencies. More if it comes to medium access, for example. Medium access, completely independent, no matter what frequency you use. So you will see 5 gigahertz and 2.4 gigahertz, they use exactly the same medium access. And this wireless local area network was even available at 900 megahertz in former times, so yes. Then just to make the picture complete, there are also metropolitan area networks, or there were some, I would say 5 to 10 years ago. There was a huge initiative called WiMAX, WiMAX together with some mobility extensions, etc. So broadband wireless access, this has been more or less completely, well, there are some WiMAX installations, but more or less replaced by LTE. Because today you say, why should we invest in yet another technology? So now WiMAX, I would say, yes, there are some installations, but in the end, it's more or less now LTE. So we will focus on wireless LANs and wireless personal area networks. That's enough. Okay, wireless LANs. Yes, we all love them. Why? Very flexible. So at home, no cabling, nothing, spontaneous setup. You just sit on the couch, lying in the bed or whatever, and you can surf the web. You don't care about cables, so very flexible. You don't have to plan, so you can also do spontaneous networking. So if two devices meet, they can set up a connection, device-to-device connection, without any planning. So you don't have to plan a base station somewhere. Don't need these things. I remember, I would say 15 years ago, Sony came up with a PlayStation Portable, a small PlayStation. Very simple to set up a network between the PlayStation to play together. Wireless networks. No big difficulties with wiring. So, and those networks are very robust against disasters. Why? Typically, you do not use direct antennas. If you start using cables or directed antennas and you have an earthquake, maybe you remember the big earthquake in Haiti 5, 6, 7 years ago, I don't know, something like this. No classical network survived this, but also no mobile communication system survives this because of those directed links. So the first things the first responders did was setting up wireless networks. That's the first thing you do. The problem there was that all those organizations, they set up their wireless networks in an uncoordinated way, creating a lot of interference. So it was a little bit bizarre. So I think in the end, the frequency coordination was taken over by one of the US Navy ships outside the island, outside the capital city, something like this. So it was a little bit more complicated, but still, wireless LANs, that's the first thing you can do. Not the best quality, but it works. Omnidirectional antennas, you don't care, you don't have to direct the antennas. That's quite good. There are also some disadvantages. Yes, the data rates are way lower compared to wired networks. Although the devices claim to be able to go up to 768 megabit per second, you will never get this. As I already told you, I see 46 other networks. And as soon as they start downloading files or watching TV over the wireless network, etc., the data rates drop. And finally, the connection even breaks, so you don't see your network anymore. Why, I will explain later. So it's a shared medium. We have lots of interference. And although you have good shielding around your microwave oven, try switch on your new microwave oven, have a wireless LAN close by, you will see a dramatic decrease of the data rate. Sometimes even the connections drop. So try watch TV over your wireless LAN, then switch on your microwave oven, etc., etc. You will see a dramatic decrease. So then, if we go to higher data rates, there are some standardized solutions, but there are also some proprietary new solutions. And standards, they always take your time. And the problem is, we have to live with the fact that we mix newer standards and older standards. And as soon as the networks detect that you have some of the older devices there, they fall back to the older standard. So that means, for example, your several hundred megabit per second device suddenly drops back to 10 megabit per second, only because your whatever device only is able to do 11B. So there are some toys we know, they have built in wireless LAN, but a pretty old standard, cheaper, old devices. So if you have one of these toys somewhere around in your apartment, the whole network suddenly has to fall back to the old standard. So this is why sometimes it's a good idea to get your high performance devices on 5 gigahertz and let all the old devices stay on this 2.4 gigahertz. We have to follow many national restrictions. I don't think that all of you know that the devices you have and you operate in Germany, for example, they cannot operate the same way in the US because we do not have all the channels available in the US. We can, for example, at 2.4 gigahertz, we can use channel 1 to channel 13. In the US, only channel 1 to channel 11. Channel 12 and 13 are not allowed in the US. Okay, there are some minor differences, but still differences. So, and Japan is still different than France and Spain and this and that. So there are some slight differences here and there. The devices know how to handle this, or you can also simply ignore it. The devices still work. Okay, so there are certain design goals. Yes, it should be possible to operate them all over the world. You don't want to replace your radio modem only because you enter another country. Low power, battery use. That is a special requirement. Yes, we can transmit multi-megabits per second, gigabits per second, whatever, but still the devices are battery operated. That's a problem. So try to sleep as much as possible. That's true for wireless LAN, for Bluetooth, that's the same. No special license, yes, robust, easy to use, that's important. Easy to use, simple management. So plug and play. And for many people, it's even too complicated to enter passwords for whatever, WPA2, encryption, blah, blah, blah. Oh, what does it mean? So this is why your router, for example, offers QR tags, and you take a picture, or you push a button on the router, a WPS button, and then for the wireless protection system, and then you can enter in this short time span, you can enter the network and these things. Because what does it mean? Encryption key setting up, or is it WPA2 enterprise or not enterprise, or this or that? It is complicated, and even for all of us, if you try to use your Android device, enter eduroam here. oh, what kind of, oh, is it done automatically, this and that, or are there problems? And then finally you end up with broadcasting your password and all these problems. We'll come back to this. Security is a big issue. So do you hide your SSID, so your identification of your network, or not? I will come back to this. Privacy. So can your neighbor actually eavesdrop into your communication, yes or no? How does this work? What can your neighbor see and all this? Because everyone can operate the devices, and you can switch your device in a so-called promiscuous mode, which means you will receive all wireless LAN packets, no matter if they're intended for your device or not. Then you use tools like Wireshark, and you can easily look into all packets transmitted. Okay? Because here suddenly we have a laptop and we can control everything. With a mobile phone it's a little bit more difficult. It works on wireless LAN, but on LTE, where are the tools where you can actually, well, scan the frequencies? Not that simple. With wireless LANs, very simple. Very simple. You can simply do it. So, okay. And then the last point is it should be completely transparent. So, for the higher layer protocols like IP, TCP, or whatever, you should not even notice that there's a wireless LAN. Well, it's a connection somehow. Someone transports data. If it's Ethernet or wireless LAN, we don't care. But at the same time, sometimes it might be useful to know where your device is. You have to handle this somehow. Because if you move across the campus here, you stay in the heteroome system, and somehow the system still is able to transmit the data to you, but you can be sure we do not broadcast your data over all 1,800 plus access points. But there's a seamless roaming possible. So be aware what we call handover or handoff in the context of mobile telecommunication system, 2G, 3G, 4G, is now called roaming. So when we talk about roaming in wireless LAN, this actually is a handover between the access points. And roaming in GSM world, GSM UMTS LTE world, was handing over a connection from one operator to another operator. That was the roaming, national or international roaming. Here, roaming is actually a handover. Well, it's not my fault, but that's the terminology. Okay, so easy, simple, transparent. That's the design operated by you. Now we have three topologies for our wireless LAN. The classical is here on the upper left-hand side. It's called an infrastructure network. Why? We typically have an infrastructure, a wired network. A wired network with access points. The wireless LAN standards do not say anything about how you structure your wired network. The standards do not care. If this is a switch network, if this is again a broadcast network, if this is again a wireless network, if this is a fiber optics or whatever network. Wireless LAN standards only specify what the access points have to do, but they do not say anything about the infrastructure. Nothing. Usually this is a switch network. Some kind of an Ethernet switch and some Ethernet cables to the access points. Here, for example, it's a little bit different. It's a different solution where you have kind of wireless access centers where all the antenna, the signals, they come together, the data comes together at a central point, etc., etc. This has some advantages on larger deployments. So that's usually the infrastructure you have at home. You have your DSL router, and the DSL router then has the antenna. Or you have DSL router and a switch or an integrated switch, and then in another room you have another access point. You have better, higher data rates or something like this. And your devices, they then connect to the access point. And we will exactly discuss how this works, how the medium access works, and how you connect your device to the access point. So that's called the infrastructure network. But wireless LANs also support so-called ad hoc networking. You see here two networks, ad hoc networking. So you can come together and you can spontaneously transmit data without prior setup of an infrastructure. That's called an ad hoc network. A typical characteristic of ad hoc network is all the devices have to see each other. The classical wireless LAN ad hoc network cannot forward data. So all the devices have to see each other and then you can transmit data. In this scenario, the two devices can transmit data and the two others, but not the two on the right hand side. So that's one of the classical settings. And then a newer mode of operation, so-called mesh network. So there are newer standards in the wireless LAN standard family that describe how you can set up a partially meshed network. The classical ad hoc network has to be fully meshed so that all devices can talk to each other. You have to have a direct link, a direct way of wireless communication. For the mesh network, you can communicate via other devices with the device. So there's some routing integrated. Routing, layer 3, no, here, layer 2. So here the layer 2 can perform some routing. This is not really internet routing, layer 3. That's similar to what your switches can do. The switches can also set up a kind of tree, for example, and here you can also find a path in these meshed networks. So these are the three topologies, and the most common topology is the so-called infrastructure network. That's what you usually have at home. You can also use ad hoc modes. That is, for example, that's an annoying example, what some printers do without naming the brand, but there are some printer manufacturers, as soon as you switch them on, they try to set up an ad hoc network. How do you notice? If you scan the list of available wireless LANs, you always find the printers of some neighbors or some printers or some other devices, and these are devices that try to set up a spontaneous network. Hey, I'm this and that printer, please connect to me, please connect to me. And then, yes, depending on the model, you can send something to this printer, print it then out at the neighbor's printers, but that's a different story. So, okay, ad hoc networks used, yes, but usually you set up infrastructure networks. For us, it doesn't matter. We will mainly discuss the medium access here. That's the important part here. That's also what we looked into with the other technologies. The medium access here. How do you control the medium access? Is this now a CDMA, FDMA, TDMA, whatever scheme? We will discuss this. So infrastructure, ad hoc, and a little bit newer, mesh networks. Mesh networks will be very interesting for disaster recovery, for example. If you have an emergency response team entering a site after earthquake, after fire, this mesh network is very interesting, but it's more complicated. But that's where we do, for example, our research in this mesh networking. Okay, these are the scenarios, and as I said, we will focus on the mainly the wireless access, medium access schemes. So now, yes, new technology, new terminology. This is how the standard sees our infrastructure network. So the standard says, well, we have many stations. That was what the other standard called mobile station or user equipment. Here, IEEE says these are stations. Stations, no matter what this is. For historical reasons, I don't know if any one of you knows what kind of device this is and the manufacturer. Yes. We were in elementary school at that time. I don't know. Apple Newton with these two ears. That was one of the first trials of Apple to come out with a handheld device. So Apple Newton, very interesting. Many years ago, I don't know, 20 years ago or something like this. No, not really 20. So stations, laptops, tablets, smartphones, whatever. We have stations and with an access point. That's typical for infrastructure. The access point starts spanning a basic service set. Don't mix this with base station subsystems. That was GSM. Here it's called basic service set. a basic service set is identified usually by the service set identifier. So that is what you see when you switch on your device and you see those different names of wireless LANs. Then you see the name of such service sets. So that's a basic service set. You have an access point and you have devices there. What is important here is the device has to see the access point. That means it's be able to receive and transmit to and from the access point. Those devices, they don't have to see each other, but both have to be able to send and transmit to the access point. So the access point defines a basic service set. How? I will explain. So we have other access points. Here you see the other part, you see another access point setting up another basic service set. Yes, access points can also set up several service sets, but here in this example, 2 access points, 2 basic service sets. So now, we could have different identifiers for those 2 service sets, but to make life simpler for you, when you operate different access points at home, or here where we operate 1800 access points, we can combine them to something that's called an extended service set. So we form a logical network, this ESS, a logical network comprising different basic service sets. So we have one logical network and we can give this logical network a name, and that's the name you see, for example, EduRoam, for example, Funkland, for example, guest network, for example, whatever. And then it does not depend if you're connected to this access point or that access point. Usually we have the same passwords, etc. But we operate, as we will see, on different frequencies. Because it's not wise to overlap different networks. You can do, because no one controls this, and that's one of the differences. Remember? 2G, GSM, the network operator has to take care that those cells, if they overlap, do not use the same frequencies. Here, tough luck. If your neighbor picks the same frequency as you do, okay, we pick the same frequency. Then we have interference. Okay, you cannot do anything against this. Yes, your router tries to avoid the frequencies, but if I check, I've got something between 8 and 12 networks on single channels, so what to avoid. You try to avoid this, but, and that's typical for wireless LANs, you can operate different networks with different names, different identifiers on the same frequencies, because this is not regulated. And we will see what happens on the MAC layer if those 2 networks send at the same time. Collision, destroyed data. That's it. There's no guarantee, so no one cares. So if you have many networks operating on the same frequencies, you have a lot of collisions, a lot of interference, and your data rate drops until it doesn't work at all anymore. So what happens if the neighbor picks the same name? Yes, your neighbor can even pick the same name. No one controls this. This might confuse your devices. You can do this. Just try it. Name your network exactly as your neighbor does. Then your the devices of the network, if you have a stronger signal, will try to connect to your network. Yes, because same name. What's the problem? Well, it's not a controlled system. Okay, then we hope that at least the passwords are different. But if it's not password protected, and then your neighbor devices think, this is a stronger signal, they go into your network. Yes, this works. It's not a controlled system. So usually most of the networks today, they are password protected, and then the devices will try to connect, wrong password, that's it. But you can completely confuse the devices because they always try, but password doesn't work. But this is my network, I try it, but password doesn't work. So yes, you can completely confuse everything, and so you have to talk to your neighbors if someone does this. Okay, but no one controls this as long as you stay within the maximum output power. Okay, so so you can set up a larger logical network using the same name. How to create the name, etc., etc. I will come back to this SSID thing and where do you place this SSID and what is this SSID? Where do you see this in the packet? I will come back when we discuss the layer 2 packet format. There you will see the SSID. Okay, so what does the standard cover? The access point, the medium access, how you span the BSS, how you set up the whole ESS. The standard also defines the basic functions of a portal. It's called a portal. The portal connects this, however it looks like, wireless network to other local area networks. So how do you translate a layer 2 packet from the wireless into the fixed network 802.3 Ethernet format? Because what you see here in this light pink, it's a 802.x local area network. So a fixed network following Ethernet, usually Ethernet standard. So you have to translate the packet formats because the packet formats are a little bit different. And then there's something shown yellow here where the standard says, and then there is a distribution system in between. The standard does not specify the distribution system. The standard only says the distribution system has to be able to transfer packets between access points and between access points and a portal, depending on the MAC addresses. But the standard does not specify how. So, for example, this could be a switch Ethernet system in between, or this could be some fancy proprietary system all integrated in your cable modem or DSL router. Because what you all see here is typically integrated for the usual home deployment in one device. Your DSL router, your cable modem has all this integrated because usually you have several, Ethernet ports and you have a wireless LAN connection. So this portal functionality is integrated. The distribution system is integrated in your device and your router knows how to handle when a packet comes into the Ethernet port and the destination is somewhere on the wireless LAN and vice versa, or when it comes from a wireless LAN, it has to go to a wireless LAN, or if you set up 2 different wireless LANs at the same time. So most of the devices today, they can set up at the same time different wireless networks at 2.4 and at 5 gigahertz. So I'm not aware of devices that it can set up 2.4 networks at the same time. Sure, it's possible. But usually you set up your wireless LAN at 2.4 gigahertz and at 5 gigahertz, and that's it. Yeah.
What is again the ESS or EES?
This ESS, Extended Service Set, that's the name in the standard for this logical network that comprises different basic service sets. So if you set up a larger network, maybe one access point is not enough at home. So you need 2, 3, 4 access points, or like here, hundreds of them. But you do not want to tell every one of you, oh, if you're in this room, you have to use this identifier. If you're in that room, you have to use that identifier. So you stay with the same identifier, no matter which access point you use. So you set up a kind of a logical network that contains different access points. How you do this, more on this later.
Are these access points then repeated or?
So the question is, what are the access points? Well, in the standard, these are basically components that receive data from a distribution system and are able to transmit and receive this data following the 802.11 standard. The standard does not say anything about how you implement the distribution system. So this could be a bridge, a repeater doesn't work because in the distribution system, this is typically in different technology. Repeaters can only repeat between the same technology. So at least you need bridging functionality. Bridging from one technology to another on layer 2. At least a bridge. A repeater is not sufficient here. You can buy wireless LAN repeaters, but that's something different. A wireless LAN repeater, depending on the setting, can be a completely stupid idea or a good idea. Wireless LAN repeaters, they extend the range of your network. But that's the stupid way of setting them up, is they receive on a frequency and transmit on the same frequency. And this halves your capacity. So it's better to have repeaters receiving on one frequency, transmitting on another frequency. That's better, because otherwise you have data rate. But there was another question.
No.
Okay.
So this would be then one access point in this language, or?
Yeah, that's one access point. So the standard here, repeaters are basically invisible. So they do not increase capacities or something like this. No. Oh, so that's the standard point of view. So you have to distinguish between, okay, that's what the standard says, and then I have my implementation with everything. The standard also does something similar for these ad hoc networks. It's also stations, but then it's called the independent basic service set. Okay, no big deal there. So in the end, also if you set up an ad hoc network, the ad hoc network will get an identifier identifying the ad hoc network. But identifiers are not for security purpose, not at all. Just pick the identifier your neighbor has. Okay? So, a little bit more complicated is if you look at a mesh network. So what you basically have is, this is kind of my infrastructure network, so access points. That's what we already know, access points and networks. Then there's this magic distribution system. Also there, we have access point distribution system portals. And what is new is you can set up the functionality of a mesh gate. Again, this functionality can be integrated in your DSL router. It's just from a standardization point of view, that's a different functionality. This is why it's separated. So we can set up a mesh gate. Mesh gate only translates between the mesh network and distribution system. So, and then we can form a mesh BSS. And the mesh BSS then knows how to forward data from device to another mesh gateway. This is how you set up this. And all this can be co-located on one device, but that's an implementation issue. The standard separates the functionality. So the standard says with a mesh gateway with certain functionality, with access point with certain functionality, a distribution system, but all this can be one device. So there are devices that are basically gateways into mesh networks plus access points plus distribution system all on one device. That means you can place these devices wherever you are. They can connect to other devices forming mesh networks, but other devices can also connect to these access points, and they think, this is a nice infrastructure network. But in reality, it's not a complete infrastructure network. It just looks like an infrastructure for these networks. But then you have maybe a disaster area, earthquake, etc. You set up these mesh stations, and then again you have other stations, and sooner or later you have a portal that connects into whatever infrastructure. That is the idea. And what is new here is that you have possibly redundant paths. So you have different paths through this mesh network, all on layer 2. We are not talking about IP routing. We are not talking about networking, IP addresses, whatever. This is a pure layer 2 technology. So that's a newer characteristic of this wireless LAN. We can form mesh networks, and there is, yes, we have to find the paths. We cannot use internet routing because we don't have IP addresses at this level. So this is why there's a so-called hybrid wireless mesh protocol, HWMP, and this protocol performs this. Well, we have to find a path through the mesh network. We have to maybe switch to another path if a path breaks down, etc. So this is there are new capabilities, but I'm pretty sure most of your devices cannot really do this mesh networking. So there's no implementation for many of the devices, but there are some, and this would be quite a good idea to get better coverage, for example. not only for disaster areas, also for buildings. This could be used if you do not have cabling. But always be aware, if you have a cable somewhere, use the cable. Don't go for wireless if you have a cable, because it's never as good as a cable, if you have a cable.
When you said most devices won't be able to use this,
Yep.
doesn't this mean that this would be hardware?
No, software. So basically, because there's no necessity for most of your smartphone, for example. Why should your smartphone be a mesh gate or a mesh station? So yes, you could implement this. There are implementations, but normally your smartphone only acts as a station that is able to connect to an infrastructure. Many devices are not even able to form an ad hoc network. That requires additional software. Yes, not hardware. No, the meet access schemes, etc., that's the same. But it requires a piece of software that actually receives data, processes, and forwards data. And that's usually something you do not do as a smartphone or as a tablet or whatever, because you just connect to a base station and transmit data. So it's not new hardware, it's just software. But there are implementations. Enough open source, etc. implementations, so that's not the point. So these are the three configurations: infrastructure, ad hoc, and mesh. And this is the standards point of view and the names the standards have for this. Okay, I know that's quite a lot to understand all this, but I will always come back and we will focus on the infrastructure. Why? Because this is what 99% of the installations use, is the infrastructure, the simple access. And already there we see interesting features when it comes to the medium access. So what do we cover? Not a big surprise. The standards, all the higher layers you already know from telematics. That's the classical TCP and IP. There's also hidden the logic link control. That's where in telematics I said, oh, you don't really see it, but yes, there's a type length field in the Ethernet packet. Not that important here. And then the main difference is here: medium access control, because there's no wire, and pretty sure the physical layer. So the usual setting is the following. You have your 802.11 wireless LAN MAC, wireless LAN 5. You go over with the wireless link to your access point, and here you see the access point usually has to act at least as a bridge, and then this access point has to translate 802.11 MAC, translate into 802.3 MAC. So the Ethernet packet format, and then we follow the classical switch Ethernet or whatever, as we know from telematics. So that's classical. So the new part, and this is what we cover here in this lecture, is the 802.11 MAC and physical layer. Those two layers, these are the important layers. And that's one of the key features. The higher layers are all the same, because otherwise you would have to replace all the higher layers. That's not really a good idea. Okay, so you see, only the lower layers they're affected by this wireless idea. So there you find in the standards, this is where I will not go into all the details, even more sub-layers. They deal with different access mechanisms. I will look into this a little bit. Some synchronization, roaming, the handover between stations, and then many other functions you need now because it's a wireless system. So carrier sensing, not important in switched Ethernet anymore. That's interesting. Modulation, coding, these things. Channel selection, not important if you have a fiber or a twisted pair, whatever. But here I have to pick channel 2 or channel 11 or this or that. This channel and management and coordination of these functions. Wake-sleep patterns. Here it's important to save energy. So we have to put the device into sleep mode very often to save energy. All these things. So I will not go into all of the details, just to pick some of the important features to show you the difference to the fixed networks. But this is all left for the next week, so I wish you a nice day, and thanks a lot for today. So, good morning and welcome back to mobile communications. the last time I started with wireless LAN. So wireless LANs, to repeat with the key characteristics, typically local scale, under private organization, under your control, so you can do whatever you want, more or less. You just have to follow certain restrictions like maximum output power, for example. Okay, so you cannot set up a wireless LAN covering your whole neighborhood, for example. But then there are some restrictions when it comes to frequencies, but that's more or less all. So it's not like the big mobile telecommunication systems where you say, okay, on these frequencies we use TDMA, FDMA scheme, or here we use CDMA scheme, or things like this. But here it says more or less, okay, 2.4 gigahertz, for example. And then the standard for wireless LANs, the standard defines the architecture. So what is the infrastructure mode, what is the ad hoc mode, how can we set up mesh networks. But the standard does not describe anything regarding the fixed infrastructure, only mainly the radio interface. So today we will cover the physical layer, some key characteristics, and then especially the MAC layer. Because you might remember from telematics, MAC medium access control is quite boring when we have these star topologies, structured cabling, a switch, and then all the hosts connected in a star topology with this switch, and then many switches, again star topology, again with a bigger switch or a router. Quite boring because we always have full duplex connections between the end system and the switch. So there can never be any collisions, maybe some congestion on the switch, but not a collision. So that's what we have today in cable networks. Here it's completely different because it's wireless. We always have collisions, all the time. Okay, so we start with the physical layer. All this wireless LAN technology started early 90s, mid 90s, and at that time, so the first specification for physical layers, we can call them now historical because not used anymore. The first specifications, they covered 2 radio and 1 infrared standard. Maybe you remember, you've been little child, there was these mobile phones with infrared connections. Today we all have Bluetooth. There's no IRDA interface or things like this, so no Bluetooth. But at these days, so we had infrared, so we could basically face 2 mobile phones to each other, and then we could transmit business cards, things like this. Okay, so infrared was quite interesting, and the interesting part is that we are now back to, using light for communication. Now today it's called visible light communication, way higher data rates. So infrared, this IRDA interface, at that time that was up to 115 kilobit per second. Now with visible light communications, we are at 500 gigabit per second, so that's a little bit different. So this all started with these very simple physical layers, so frequency hopping, and then the most successful specification was the direct sequence spread spectrum. So DSSS was a scheme that used different modulation schemes depending on the data rate, so 1 megabit, 2 megabit per second, and then a fixed chipping sequence to spread the signal, so-called Barker code. A Barker code has special characteristics, so if you perform this autocorrelation, then so that means you compute the inner product, assuming these are vectors, and if you shift the Barker code on top of another Barker code, say Barker code, then suddenly, if you have a perfect match, you get a very nice peak if you calculate the inner product. So this is used for very good identification of the signal. So you spread it, narrowband interference and all these problems, and that was the first idea. And then we had some limitations, so 100 milliwatt, for example, maximum radiated output power in the EU, 1 watt in the US. So all you basically did is you buy the US cards, and that you had better range of your wireless LAN. So this was the early days of these systems. But already in these early days, the basic format of the physical layer was standardized. So I will not go into details because this is historical, so legacy. But there you could already see, we need a lot of synchronization. So before you start with your data, because you have no synchronization at all, compared to, for example, GSM. If you look at GSM, you know this is my time slot, I'm time synchronized, so I know exactly plus minus guard spaces, time advance, etc. But I know this is my time slot. Here, I don't know. There is no strict synchronization by a base station. So this is why you need a longer preamble for synchronization, and then a standardized start of frame delimiter. And this start of frame delimiter up here tells now the system, now everything starts. And now we start with control data, so special data that tells you the modulation scheme, for example, the length of the payload, and a certain checksum here. And then we have the real payload. We will look into the payload. This is then the MAC packet, similar to an Ethernet packet. So you see, you need a little bit additional information because now we are in the wireless domain. So we need this preamble, we need synchronization, we need an additional checksum to protect the header. So this all started, the first cards we had in the mid-90s, 2 megabit per second. Okay, and then pretty soon, and now these are the standards still in use, the classical old standards. Pretty soon, a higher data rate was possible due to better integration, new chips, etc. And this was called 802.11b. So if you look into older literature, you will find 802.11b. That's the fastest standard for 2.4 gigahertz. This was then called high rate direct sequence spread spectrum. And again, you see, in this case, two different formats on the physical layer. So without, again, going into details, what you see here is that this is very typical for wireless LAN technology. We have, again, this header, synchronization, checking signal strength, length, checksumming, and different of these things. Also telling the system which data rate to use, 1 or 2, the old data rates, or now the new data rates, 11 megabit per second, depending on the signal to noise ratio. And what you also see is that the headers operate, the classical headers operate the lower data rates, 1 megabit per second. So if you now think calculating the possible data rate of a wireless LAN system, using this technology, you cannot simply say, oh, great, I've got an 11 megabit per second system, 11 megabit per second, oh, great, takes this and that seconds to download something. No, all your data packets, they start with 1 megabit per second. Why? There might be some legacy devices in the network. At that time, some 1 or 2 megabit per second devices. And to synchronize also means to send something on the physical layer, and this helps for carrier sensing. So all these devices, as we will see, they perform carrier sensing. But you cannot sense something you do not understand. You might think, oh, maybe there's noise, okay, by some whatever machine or whatever microwave oven. So I don't care, I can still try to send. No, it might be another device sending at a higher data rate. To avoid confusion, all these devices have to start with a lower data rate, and then they can jump to the higher data rate. But that also means you cannot have 11 megabit per second all the time. Because you start, you see here, for 192 microseconds at 1 megabit per second, and then you can go to 11 megabit per second. So if you now look at many packets you send, you always have this 1 megabit per second, plus you have the overhead, plus we have a lot of overhead here in the payload. So in the end, the user data rate, and that's what it says here, the user data rate, the maximum achievable data rate, if you have no older devices in your network, it's about 6 megabit per second. So that's a little bit, that's a problem of these wireless technologies, that yes, you announce them with 11 megabit per second, user data rate 6 megabit per second. And this is the maximum data rate without any collisions, without waiting for other devices, etc. That's the maximum achievable throughput. So that was one of the reasons. Also, we see a shorter frame format with only 96 microseconds. So if, then that's optional, if we do not have these older devices, we can use a shorter preamble, shorter header on the physical layer, and then directly go to the higher data rates. But still, well, you cannot say, okay, we have 11 megabits per second all the time. So this is an older standard, but if you check at home for some of the devices, you might find, especially some toys or some cheaper devices, they still follow this 802.11b, or today it's called high rate direct sequence spread spectrum. Okay, why this change in names? Well, the standardization started with 802.11, and then we had A, B, so B was first in the market, then A, and many other standards, and then this was all put together and said, now this is the new 802.11 standard. So the IEEE put all these things together. At the same time, when defining the packets, you have to define channels. And these are now exactly the channels we also use today. If we operate our system at 2.4 gigahertz, we can use up to 13 channels in the EU, and US up to 11 channels, but not the higher frequencies. So now you might think, okay, great, 13 channels. Why do I only see 3 channels? The problem is the channel definition, all the different channels, and the available spectrum, I mean, is independent of this very concrete standard. That's the ISM band. Okay, 2.4 gigahertz up to 2.48 and a little bit gigahertz. And now wireless LAN says, okay, I define 13 channels, but I need 22 megahertz. That's what you see here. So you need 22 megahertz. That means if you use all the channels, you create overlapping channels. So that's channel 2 and channel 3 and channel 4 and channel 5, etc., whatever. So you create overlapping channels. Is this a problem? Well, yes and no. If you operate at the same space, the wireless LANs, then it is a problem. Because if you have an overlapping channel, you create interference for the other networks. Interference means maybe you destroy the signal. Only with non-overlapping channels you can guarantee that there's no interference if you operate the wireless LAN exactly the same space. So if your neighbor uses a different channel, well, then it depends on how much concrete there is in between, if it's wood, concrete, steel, or whatever. What is the distance between the base stations? If you operate several wireless LANs, I mean, in a similar space, then you should use different channels, like channel 1, 7, 13. They are non-overlapping, or 1, 6, 11 if you do not have the channels 12 and 13. So then they are more or less non-overlapping. So that's one of the problems. You cannot simply use all the channels. Well, you can, but then you create interference if you send at the same time. And well, as I said, it's not coordinated. So today, your DSL routers with wireless LAN adapters, they try to coordinate this. So especially if you have the device from the same vendor, they sense the spectrum, they analyze the spectrum, and they try to avoid crowded channels. But if you have many wireless LANs, everything is crowded. Okay, this is where all these channels come from, and you have an ISM band, and you must not use higher frequencies or lower frequencies, so that's simply not allowed. It's feasible, sure, you can build these types of adapter, but it's not allowed, and you will not find commercial devices for this. So, okay, so these are the channels, 2.4 gigahertz. Today, completely crowded. At the same time, and originally the group started earlier, this is why they have 11A as a standard. Today, integrated, a group started for standardization at 5 gigahertz. And they use a different scheme called OFDM, orthogonal frequency division multiplexing. Completely different scheme. Today also used for many other technologies like LTE, etc. And already this standard promised to have up to 54 megabit per second, depending on signal to noise, etc. So the user throughput is then in the end up to 32 megabit per second under ideal conditions. Low noise, very short distance. So if you try to do this in indoor environments, well, you can set up this 54 megabit per second connection up to 5 meters, something like this. So not if you go outside on the lawn, for example. So the frequencies that can be used there, you see, it's not one frequency band, but as you can see here, there are several parts of the spectrum. They might be used for this, and they have different restrictions. The devices know these restrictions, and you can try to place your channel in these free ISM bands at 5 point something gigahertz. You see again, if you look at the packet format, once more, we have a header that at least in parts always has a lower data rate, 6 megabit per second, already higher than this 1 megabit per second, but first a preamble so that everyone knows, okay, I do not transfer any bits there, a preamble, everyone knows, aha, someone is sending and can synchronize, etc. Then the header, and then variable data, and you can then directly after this signal part, you can jump up to 54 megabit per second, and then you have some more service fields, tails, padding, etc. And then your payload, which is not the IP packet, but the MAC layer packet, as we will see. So that was the situation, basically end of the 90s, that we had these two new standards, 11B at 2.4 and 11A at 5 gigahertz. And all the devices you use, they know how to handle these older standards. Not very high data rates. Okay, so that was the physical layer, and that's basically the fallback all the devices can use if they operate at 2.4 gigahertz or 5 gigahertz, and there's a lot of noise, bad transmission conditions, they can step back to these standards. But you will have a throughput problem in your network if you have devices that can only handle these older standards. If you have 11B devices running at 11 megabit per second, they actually pull down the whole network to this lower data rate. That's a problem, because when we now look at the medium access mechanisms, we have to follow certain rules that all the devices can hear our signals, and that's a little bit more problematic. Okay, that's the classical physical layer. And also at 5 gigahertz, you have channels. Here only shown for Europe, a little bit different in the US. So here we have many more non-overlapping channels. You see here 16.6 megahertz, channel 36 for example. And yes, there's also channel 37, 38, 39, 40, but they would overlap. So here you have a much wider choice of different channels. So if possible, go to 5 gigahertz, because then you will, at least today, almost always find an empty channel. It might be the case that some of the channels are blocked due to radar. And if you look, for example, at your DSL router, what is the spectrum use? You might find a situation that your router tells you, oh, these are the channels I can receive, and I'm occupying right now this part. What does this mean? Today, and these are the newer standards, the wireless LAN systems can use several channels, a larger part of the spectrum, to transmit more bits per second. So here, if we use these more narrow channels, 16 megahertz, we can go up to this 50 megabit per second. So, but we cannot go to gigabits with this narrow channel. So what the systems do today is, at least for a short time, they simply use more of the spectrum, which is allowed. You could use the whole spectrum if you want. No restrictions. I mean, you can do this. So you could also use a complete different technologies on these frequencies. It's the ISM band. So there's even microwave welding. So if you weld steel together with support of microwaves, so the output power there is enormous. Okay, and microwave light bulbs and things like this to bring light into large areas like a stadium. In the US, again, it looks a little bit different. And there are also different restrictions because some of the frequencies used by military, some other applications. Okay, the system, again, without really going into electrical engineering and transmission technology, works different at these frequencies. So basically what's done there is you create many so-called subcarriers and you put your bit stream onto these subcarriers, but you split, so to say, your bit stream, so you do not modulate one carrier, but you split your bit stream onto many carriers. In this case, for example, onto 48 carriers. So you divide your bit stream onto 48 carriers, and then you modulate these bit streams or sub-bit streams onto these subcarriers. Then you transmit, and the trick is similar to, for example, you can transmit over a fiber red, green, and blue, and there's no interference. Okay, because they are not multiples of each other, so there's no interference. So you can transmit these colors, and that's the same. Different frequencies, you can transmit them, so they are orthogonal. So they do not create too much interference, although they overlap. But to create them in a special way, you create orthogonal carriers, and then you can transmit. You have certain pilot. Pilot always means you know exactly the signals, so you can adjust your output power and synchronization to these, and then you transmit, and this is the basic technology. So if you're interested in this, the keyword is orthogonal frequency division multiplexing. Now technology used in LTE and many other technologies. So this is the way how you transmit your 50 megabit per second. No more barcode code and things we had with this direct sequence spectrum. So, and then the next step was to say, okay, 11 megabit per second, that's not that much. Oh, at 5 gigahertz, we can already transmit 54 megabit per second. Then we implement the so-called extended rate physical layer at 2.4 gigahertz. And this builds on the classical 1 and 2 and 1 to 11 megabit per second, but now uses exactly also this OFDM technology going up to 55 megabit per second. That's basically the idea, that you now apply this older, so to say, 11A technology now to 2.4 gigahertz instead of 5 gigahertz. So that's the historical development. And in the now common standard, this is called the 802.11 ERP, extended rate physical layer. So, I mean, you can be sure all your smartphones, tablets, notebooks, whatever, they know all these standards, also all these new standards. So that was 11G, 55 megabit per second. So that was, I don't know, 10, 12 years ago, something like this. And then, again, there was now a newer system, so-called high throughput, is now also integrated in the 11 standard. And this was the old 11N standard. Don't be afraid, you don't have to know all these detailed standards. I just want to show the history that you understand why we have the technology we have today. So that now again basically uses this OFDM, but, and this is what I showed you, now uses up to 4 streams. So 4 different streams with different technology in this 20 megahertz bandwidth, and you can also use more 40 megahertz and the newer standards AC. I will come back to this later. Now using even more megahertz, and they can offer up to this 600 megabit per second under good conditions. With 11N, I haven't seen devices offering this, but okay. And you see, now we have many more of this physical layer fields in the header, because it's way more complicated. You see training fields, short training, long training, and whatever different, a lot of this training, because at these higher data rates, it's very complex to create some kind of synchronization with the bit pattern. So you see, this is just for reference, there are different types of protocol data units on the physical layer. So that says physical layer protocol data units. And you have the classical data units. This is called a non-high throughput physical layer data unit. You have a mixed, that means you have classical devices and newer, or you have so-called greenfield formats. Greenfield, that means you operate on the green field, so there are no legacy devices at all. Then you can send with complete new formats. That's the basic idea, and you can find all this in the standards, IEEE, on the web pages. So again, don't look at this whatever microseconds. You just should get this feeling of, this is the historical development. So the physical layer is faster and faster, but still we have slower fields in there, and we have a lot of additional data signals we send, which is not user data. That's the important part. So if you think, my new device, 600 megabit per second, not user data, because you see, this is my data field here, this is my data field, but still in the data field we have the MAC packet. MAC packet has MAC addresses and this and that, and then we have the IP packet. Then we have IP addresses, this and we have TCP packet. TCP header, and in the end, finally, you have your user data. So it takes a little while before we really reach 600 megabit per second for the end user data. Okay, and together with this, I will show again the important part. Together with this, we have a new standardization of a MAC layer. And that's now the more important part for us, is how do we actually access the medium? Yes, somewhere this is physical layer, okay? We learned there's a lot of overhead, synchronization, preambles, etc. We learned we have a problem if we have legacy devices there. And then we have data. But then there's still MAC. So the MAC layer has a core part, and this is the core part we will look into. The core part is the so-called distributed coordination function. So what does it mean? It's distributed. That's important. What is important about being distributed? We do not have a base station controlling medium access, but it's distributed. All devices are more or less the same when it comes to medium access. That's important for you to remember. Big difference to GSM. GSM, we have a base station, synchronization, medium access. And if the base station says no, you're not allowed to access the medium. Here, the core of the medium access is a distributed function. So the base station, and many students get this wrong somehow, and they say, the base station grants access to the medium. No, not in the core function. So the base station has the same problems as all of the devices you have. It's a distributed function in the core. If we need some special mechanisms, we can put this on top. But that's a different story. So the core, and this is what I will explain in some more details, is a distributed function. Distributed coordination function. So that means we have an algorithm that is somehow distributed over all the devices, and this distributed algorithm somehow coordinates the medium axis. There is no special role of the base station. I have to repeat this because this is done really so wrong by many of the students. They think, aha, there's a base station, we learned the GSM, base stations control, not in wireless LANs. So, if we need some special functions by the base station, for example, to offer quality of service, then we can put a special function on top of this. There was some, I would say, some special contention-free scheme, point coordination function, I would say legacy, not implemented, not used. So this is why we have a dashed line. So we have also some specialized, so you see prioritization with quality of service or some other quality of service. This is optional. So we could put this in parentheses. So optional. What does it mean? Optional means all devices have to know how to react if a network applies these schemes, but you do not have to apply them. We will see what this means later on. So yes, if you are a smartphone in a wireless LAN and if there are certain new functions for quality of service, you have to know how to react in a proper way, but you don't have to use it. Okay, and then there are some special mesh services. We learned that we have also mesh network. So let's put this parenthesis here. Why? This is also optional. Most of the networks you use, they use only those so-called contention services. Contention services means you have a contention by different stations. They compete for the access to the network. So kind of a fight, but with random numbers, as I will show you. So there is no single station that can dominate the network and say, okay, I control the devices. So the normal infrastructure-based network uses only the DCF, only the distributed coordination function. That's what you use here. So all the devices are more or less the same. Unless you start setting up a mesh network, which we do not have here. Unless you start setting up some kind of prioritized services, which we, to admit, have in some of the networks. We can do this for wireless telephones, for example, for our test beds, etc. But the normal wireless LANs you have in all the coffees and on the marketplace, open space, whatever, they have a contention-based system. What contention means, more in a second. So you do not have special priorities. Also, the base station has no special priority. If you want to send data and the base station wants to send data, you both have to fight for the access to the medium. We are all the same here. But the standard knows some additional features like mesh coordination functions, hybrid coordination functions, this and that, optional. So first of all, I will introduce basic functionality, because this is what you use in 99% of the cases. Yes, confusing, but that's how standards work. So many people come together with brilliant ideas, and some of the ideas influence the standards, but typically as options, not mandatory. Because the companies say, oh, okay, do we make more money with this? Not really. So let's make the mandatory part the part where we make money. So this is the access, this is the basic functionality. So that's the access to the medium. Hooray, we have it, and that's okay. Because as soon as you introduce new functions, it gets more complicated. Think of the neighbors, the 40 other networks you receive, and how to coordinate, and not nice. So DCF, distributed coordination function, is the heart of the wireless LAN medium access. Okay. So, and we will focus on this. Yeah.
Can we conclude certain advantages or disadvantages directly from this property? So, like, does this mean that in general, compared to GSM, gives wires more interference or
So the question is, can we directly conclude some pros and cons from this distributed compared to this more centralized? Yes, absolutely. So you cannot guarantee anything. That's the major point. With wireless LANs, using DCF, this distributed coordination function, this 99% of all the wireless LANs, you cannot guarantee any data rate, you cannot guarantee any delay. So with a coordinated system like GSM, as soon as you have your time slot, you have a guaranteed data rate. We know we have to fight for this time slot on the random access channel, but that's a different story. But as soon as you have your allocated time slot, you have service guarantees. You have guaranteed latency, you have a guaranteed data rate. Wireless LAN follows more this best effort model. No guarantees at all. No guarantees regarding data rates or delay. No, nothing. This is why we have these additional functions that can give you some soft guarantees on top, but not with this mandatory distributed coordination function. So that is exactly the access method we will look into, because, as I said, 99%. So, and this technology we use is also known as carrier sensing multiple access with collision avoidance. So we try to avoid, and this already tells you, okay, there might be collisions. And we do not read collision detection, because we cannot detect collisions. We'll come back to this later. The keywords here are hidden terminals. We are on the wireless, so hidden terminals. So, okay, and this is why the core technology for medium access here is called CSMA-CA, carrier sensing. So we try to sense the carrier. This might fail, but at least we try it. And we perform a collision avoidance scheme, but no collision detection. As fairness mechanisms, that's what I will explain. We have random backoff, fairness strategies, and we have some add-ons. I will also explain those. They are called RTS, CTS. Request to send, clear to send. Remember, hidden terminal problem. Hidden and exposed terminals. I explained in chapter 3, okay, if you have these problems, use RTS, CTS. A medium access scheme with collision avoidance. That's exactly the scheme used here. If your device experiences more interference, it can, and this is optional, use RTS, CTS, because this interference might come from hidden terminals. It might also be the neighbor, but then RTS, CTS doesn't help. Okay, so DCF, the distributed coordination function, is the core, as you saw on this figure on the slide before. We had point coordination function, not really used. There we have contention-free access, and we have newer technologies supporting quality of service. It's called this hybrid coordination function, and so there we also have some contention-based phase and some more control channel access. So, and there we can support different priorities. That's a technology introduced in some of the devices, can be used, but it's not mandatory. Most of UXS, as I said, is DCF, not HCF, not this hybrid coordination function. So we will briefly look into this, but that's not the main focus. And then for the mesh networks, we need yet another technology, because if you have these special mesh networks, you remember we had infrastructure and ad hoc mode, the classical modes, and then we have the meshed mode where you forward packets hop by hop, and there we need a special medium access scheme. Again, optional. So we have more or less one legacy in there, and then 2 optional schemes and 1 mandatory. And you have to understand the mandatory one. Yeah, that's what all the systems use, because it's kind of a typical example on how you can do medium access if you do not have this strict central control by a base station like GSM, like UMTS, like LTE. So all the big systems do not use this random distributed access, because this is very difficult then for a carrier to operate these networks and to guarantee something to the customers. Just imagine if someone charges you for the data you send and charges you also if you have collisions and whatever, and doesn't give you any guarantees, etc., etc. Already with the control systems, it's difficult. This is why no operator guarantees you a data rate. They always say up to this and that. They do not guarantee. So you can check, and if you have something like 30-40% less of this data rate, then you can go to the carrier and tell them, well, why should I pay for this? But if you have 10% less, tough luck. But here, if the neighbor doesn't want you to send anything, the neighbor can simply block you. And this is completely legal, so to say. Well, the neighbor always has to download on all your frequency files. That's legal. It's the ISM band. It's not regulated. Okay, so we hope that the neighbors don't do this, because then you fight back with your microwave oven or whatever. So, okay. So this is why we look into the DCF, and DCF is the interesting part, used by, as I said, 99. So, now this is the tricky part. It's distributed. So we do not have a kind of a clocking scheme by a base station. The whole medium access is built on top of so-called interframe spaces. Ooh, what's that? So we send frames. Let's stay on one frequency. Let's ignore other frequencies. So we have our non-overlapping channel. Now we send frames. Layer 2, we talk about frames, which is a packet. So, but layer 2 terminology is frames. So we send a frame. A frame, that means you occupy the medium. So let's look on this figure. So you occupy the medium is busy while you send something. And you hope, and that's only a hope, that with the help of carrier sensing, all the other stations notice this. Oh, there's someone sending on my channel. And all the devices are polite. Well, remark, all the wireless LAN devices, not Bluetooth. Bluetooth? Why Bluetooth? Oh yes, Bluetooth also operates on this frequency. Bluetooth does not know anything about the wireless LAN standards. Carrier sensing? Bluetooth? No. Why? 2.4 gigahertz? I use Bluetooth. So, okay, you use wireless LAN, tough luck. I operate on exactly the same frequencies. That's it. That's ISM band. Okay. More to this later when I also cover Bluetooth. So, all the wireless LAN devices, they perform carrier sensing. They do not send anything as soon as they receive some energy on this channel. Okay, so they see, oh, someone is sending, great, I do not send anything. So now, what has all this to do with the spaces? The medium access is coordinated by waiting. Waiting for the medium to become a free medium, and then waiting for certain times. Why? Well, as I said, we do not have any means to force another device to send or to stop or not to send or whatever. So all the devices only listening to the medium, and there are two situations. Either the medium is busy, then I'm not allowed to send, that's quite clear, or the medium is free. And then we have different options. So first of all, and that's the simplest situation, I check the medium, and if the medium is free for diffs. Diffs means DCF IFS. IFS means inter-frame space. So if the medium is free for a certain time, DCF are distributed coordination function. So that's the standard function. If the medium is free for this diffs, that's a certain amount of microseconds, then I'm allowed to send immediately. That's exactly shown here. So, if my medium is free, and I wait for diffs, and I hear no other station on this channel, then I can immediately send and occupy the medium. This is quite good because then we know we do not need any additional mechanisms for coordination of different stations. So if your laptop, your smartphone, or if the access point wants to send, and you sense the medium free for diffs, then you can directly send. You don't have to wait. You don't have to coordinate. So wireless LAN is very nice if you have an overall relatively low load, because then the medium is free for most of the time. You wait for diffs and you can immediately send. That's quite nice. So, and that's used for the normal so-called asynchronous data service. So that is the situation under, let's say, light load or an empty medium, because then the medium is almost always empty. But what happens during peak times? The medium is not empty. So, as we will see, if you check the medium and the medium is busy, and then suddenly the medium becomes empty again, so someone else stopped sending, or you yourself stop sending, then if you want to send a normal data packet, you again have to wait, and that's shown here, for diffs, at least for diffs. But, when I wanted to send, the medium was busy. That means there are some other stations. And we will see that then a station has to enter a so-called contention period. If you check the medium and the medium is busy, so for example, if you want to send here, this point, so your higher layer tells you, I want to send a data packet here. And you check, and the medium is busy, then you have to wait until the medium is free. Then you have to wait at least for this DCF interframe space. And exactly at this point, you enter a so-called contention phase. Because you know, oh, there are some other devices. So we have to fight for the access. You do not know at this point in time if there another station wants to send something. You do not know. There's no coordination. I will explain another slide with some other slides how the contention phase works, but somehow you have to solve this potential contention. You don't know if there's contention. So maybe there are 3 other stations or 2 other stations. They also want to send something. So altogether we have 3 stations. They all enter this contention phase, and now they have to wait for a random amount of time. How we do this, I will explain. So what they do, those stations, is they pick a random number and they have to wait for some time. And the station with the lowest random number accesses the medium. I will explain this how this works with another slide. So that's the basic idea. And then a station accesses the medium at this point, and again, with the help of carrier sensing, all the other stations know, oh, damn, I lost this competition, another station is now occupying the medium, so I have to wait until this station ends. I will explain exactly this mechanism in more detail, because this is the normal operation. So now, why do we have all the other waiting times here? Well, this has to do something to do with priorities. So we have different types of packets in our network. What I explained right now was sending normal asynchronous user data. So this normal data for all of your files, whatever, you use this. But it might be the case that you have to send control packets, especially as we will see acknowledgements. Wireless LANs send immediate acknowledgements after the reception of a correct packet. So if you, or the base station, receives a packet, it immediately checks the checksum. If everything is okay, it immediately sends back an acknowledgement on layer 2. For unicast packets, we have an acknowledgement on layer 2. But sending a packet, doesn't this collide with other packets? The trick is, we wait for these types of packets only, so for acknowledgement, we wait only a short interframe space, which is shorter than a distributed interframe space. So if we want to send a packet with higher priority, we use shorter interframe spaces. And an acknowledgement is a special packet with a very high priority, so it must not collide with other packets. So as soon as you receive a packet, you send back an acknowledgement. But for sending back, you only wait a short interframe space. So why is there no collision? Well, in a correctly operating wireless LAN, only one station was successful. This station sends the data to one receiver, and this one receiver immediately sends back the acknowledgement to the sender of the user data. There must not be any other station. Okay, unless we have interference, neighbors, etc. But so there must be no other station sending, and so I use short interframe space. And if you have to send normal data, well, by carrier sensing, you notice, someone else was faster. You do not know that this is an acknowledgement for whoever. And this is the way how you introduce priorities in sending in wireless LANs, by longer or shorter interframe spaces. So in the normal operation, we will typically see diffs and CIFs, so DCF interframe spaces and short interframe spaces. So that's the normal pattern. And then we have, and this is just to make the picture complete or confusing, we have some more interframe space types, and PIFs typically not used anymore. We use for different types of prioritized services. But as I explained on the slide before, this is all optional. So we will focus on diffs and CIFs. That's normally what you use in your wireless LAN. But just that you know it, there are some other interframe spaces, and they can implement quality of service just by using different interframe spaces. So if you have lower priority traffic, you will get a longer waiting time aside. And if you have a higher priority, you will have a shorter waiting time. So by adjusting the waiting times statistically, only statistically, you will have certain priorities. No guarantees. There's no guarantee. But statistically, you can assign higher priorities, for example, for voice traffic. If you have your voice over IP system over wireless LAN, you assign higher priorities, which means lower waiting times to your phone, wireless LAN phone, and lower priorities, higher waiting times to your background traffic, for example, or to your IP television, higher priority compared to your file download, etc. So this is feasible with wireless LAN. But as I said, the 99% of the traffic uses this DCF function and no priorities in addition. But some of the devices, they can handle these priorities. So important to remember from this slide is, priorities in sending are implemented via different interframe spaces. So that means via different waiting times, because there is no central controller. So this is distributed. So all the stations know how long to wait in which situation. So this algorithm is completely distributed. We will see this algorithm in operation in a second. Okay, so priorities via spaces. Yeah?
Can one check if the router is using these, or?
If the router uses these additional functions, yes. So you can easily sniff into the network traffic if your network allows this. And the sniffing tools like Wireshark, for example, can put your wireless LAN adapter in a so-called promiscuous mode. Promiscuous mode means you receive all packets, no matter if the destination is your MAC address or not, because you can receive them, they are sent over the air, and then you can analyze the packets, and then you will receive those packets, and then you will see if those functions are used.
How would I see that? So would it be signed? Would the packets be signed?
No, the Wireshark can tell you, for example, what type of packets are sent, broadcast packets, or these acknowledgement packets, or RTS, CTS packets, etc. will directly tell you. So there's a special wireless LAN analysis mode in Wireshark where you can analyze your wireless LAN. Yeah. How you enable this functionalities on your wireless LAN, for example, router access point, well, that depends. But I know that, for example, if you have certain wireless LAN voice over IP phones from a certain vendor, they harmonize with the base station. So they can implement priorities using these mechanisms. Yeah. But not for general purpose. So you will understand these priorities, etc., when I come to the example, how you then really access the medium. Just remember from this slide, so priorities implement via spacing. Well, that's really different from someone telling you now it's your turn, your turn. So now, the classical access method. The classical access method, that's the first slide, and then there's another slide with some more examples, is the method called the CSMA-CA. That's what you will find in literature. So carrier sensing, listen before talking, multiple access with collision avoidance. Because listen while talk, the CD, the classical Ethernet mechanism, doesn't work, as I explained earlier in this lecture. So, if you're ready to send, you start sensing the medium. And that's the carrier sensing. And in wireless LAN, this is called a clear channel assessment. How you do this depends on your physical layer. Do you do this on 5 gigahertz, on 2.4 gigahertz? What is the modulation scheme? What is this? What is that? This really depends on the physical layer. And this is why it's so important that you speak the same language on this physical layer, that even if you can transmit with 600 megabits per second, this part has to be understood by all participants in the wireless LAN. Otherwise, you're sending with 600 whatever megabits per second, and no one understands you, and then says, okay, channel is free, and they start sending, scrambling your data. Not a good idea. So, and then, if the medium is free for this interframe space, to be more precise in the normal case for this DCF interframe space, so if it's free, then you can start sending. But that's the normal case. Which type of IFS depends on the service type. Short, AIFS, RIFS, DFS, SIFS, etc. So normal case, it's the diffs. So, and that's exactly situation number 1. So you wait for this diff, and you have a direct access if the medium is free for diffs or longer. Then you can directly access the medium. So that's situation number 1. So, for example, here you're ready to send, you wait, and then perfect, you can start. Situation 2 is medium is busy. You want to send here. Medium is busy. So you have to wait for this certain amount of time. Diffs in our case, and then you pick a random number. Exactly at this point in time, here you pick a random number, and the random number is out of a certain interval. Okay, so you pick your random number, and then you have to wait slot time in microseconds times your random number. So if you pick a 3, then you have to wait for 3 slots, which means 16 microseconds. If there are more devices, another one here, and the other one picks a 2, then the other station waits only 2 slots, 40 microseconds, checks the medium still free, starts sending. You check after 60 microseconds, oh, bad luck, medium occupied. So, if another station occupies the medium during this so-called back-off time, this random back-off time, well, you are not allowed to send. But, and we will see this in a big example, the back-off timer stops. Why? You're not allowed to send, but you're counting down your waiting slots. So if you have picked 3 waiting slots, another station 2, that means you count down 3, 2, 1, oh, other station sending. And you store the 1, you count down. Why? You're not allowed to send in this round, but the next round, again, new stations have to pick a random number, but you can keep your old number. And because you're counting down, the probability that you have a lower number than the other stations increases. And this introduces certain fairness. No guarantees, but fairness. So you pick random numbers, and well, maybe you pick the large number, big number, other stations pick lower numbers, then, well, bad luck, but you count down. And then the next term, maybe another new station even picks a lower number than your remaining waiting time. Again, bad luck. But statistically, sooner or later, it's your turn. This depends on the random number. Okay, so this is why we have a certain fairness integrated. Okay, so you pick a random number and you have to wait for a certain number of time. So, but what happens now? I mean, depending on the random number, if you have a large interval, oh yeah, so the chances for picking the same random number is low. What happens if 2 stations pick the same random number? Guess what happens? Hey, this is the best effort system. What happens? Collision. Yeah, collisions. That's all. Boom. Okay. Tough luck. It's a random number, so if you have a small interval, the probability of picking, let's say, from 0 to 3, the same random number is quite high if you have many stations. Okay, then let's use a large interval. Lower probability. Is this a good idea? Well, if we have a large interval and you, the lucky one, picking a big number, that means long waiting time. Not a good idea in situations with relatively low traffic. So what do we do? In addition to this picking a random number, we shrink or increase the interval depending on the load. So if you experience no collisions, no collision means you will get back an acknowledgement from the other side. You stay with a small interval. If you experience collisions, that means no acknowledgement sending back, you double the interval and select a random number from the doubled interval. It's random, but at least you spread out basically the random numbers. But be aware, this mechanism is again not coordinated. No one tells the station which interval to use. Shrinking, increasing the interval, so it's kind of a breathing interval, is only based on the local experience of this very single station. Big drawback, if you are a new station without any experience, you will start with a small interval and you will be the winner. compared to the older stations picking random numbers out of large intervals. So yes, that's not really fair, but okay, who promised to be fair? So, but that's one of the mechanisms how you can adapt to the traffic load by increasing, decreasing the size of the interval. There's an upper limit, etc., but that's the basic idea. And by storing the remaining slots you have to wait, you will have a certain fairness, because then you have this kind of monotone decreasing number of waiting slots, and sooner or later it's your turn. Okay, it can be tough luck that someone else exactly picked the random number which is equal to the remaining number of slots you have to wait. Collision. Okay, that's it. So that is the basic idea of the random access. I know that might be a little bit confusing. This is why we have a nice example for this.
Question about the contention phase. You said that after I wait a certain time, after my contention phase is over, I do carrier sensing again, and then if it's busy, I reuse my old random number.
Yeah.
But how has that been? I mean, my old random number has been counted down to 0, hasn't it?
No. For example, if now let's so we do the example. Station A wants to access here, and station B wants to access here, and both see the medium is busy. So A now has to pick a random number, for example, out of the interval 0 to 15, and B, a new station, picks a random number out of the interval 0 to 3. So they both have to pick a random number after waiting for the stiffs. So, for example, A now picks the random number of 1, and B picks the random number of 3. It's random. What happens now? They now count down. So A has to wait for 1 slot, and that's, let's say, 20 microseconds. 3 has to wait for 3 slots, and that's 60 microseconds. What you do now is you count down 1 slot waiting, and for A, that's it, basically. 1 slot here, 1 slot waiting. Then A can access. But B also counts down from 3 to 2. Checks the medium. Oh.
So the medium checking doesn't have
permanently, yeah. So exactly. So okay, that maybe the misunderstanding exactly was, so you do not count down and then check the medium, but you permanently check the medium. So then for station B, this 2 remains, and then for the next turn, B can reuse the 2. But then maybe A picks the 0, and again we have a problem. So yes, you permanently check, sense the medium. As soon as it's occupied, you stop. So to understand this, we have this example. This is exactly the example you should fully understand. Why? Because then you understand what happens in normal operation on the wireless LAN. So this is why I will explain this in some more detail. So we have in this example, classical example, 5 stations competing for the medium. We've identified here with this small orange arrows the packet arrival at the medium access layer. So the higher layer, IP packet, ready, sets and tells the network driver, now I want to send the packet. Now this is the packet arrival at the MAC layer. So you see these different points in time. And what happens now? Station 3 here has the arrival at the MAC layer. What does station 3? We wait for these diffs. Wait, and then we occupy the medium. So that's the classical situation in a very light-loaded network. So you can immediately access the medium after waiting for these diffs. So what happens for the other stations? The other stations also want to wait for diffs, but here carrier sensing. So carrier sensing tells medium is busy. The same is true for this and for the other stations. So station 1, 2 and 5, all these stations have to wait because the medium is busy. Okay, now the medium is busy and we learned we have to wait until the medium is free again. That's exactly the next step. The medium is free here. And now station 1, station 2 and station 5, they all wait for diffs. Pick a random number. And now the random number here is indicated here in color, kind of a waiting time. Here called a back-off time. Back-off time in number of slots. So station 1 picks a large random number because the back-off time, the overall back-off time is quite big. Station 2, as you see, picked a small random number. Back-off time is small. Station 5, something in between. That's the overall back-off time. Now time continues. Station 2 has to wait. By the way, this is all, so to say, megabits per second you will lose compared to the maximum throughput of your network. If someone claims 600 megabits per second, not during the waiting times. And the waiting times are independent, more or less, of the speed of the network. That's waiting time. So you wait 0 bits per second. Okay, so wait the diffs, then you count down. And in this example, station 2 has the smallest random number. And after waiting for this time, station 2 accesses the medium, exactly here. So we had the waiting and then we access the medium. And now shown in green here are the remaining waiting times of station 1 and the remaining waiting time of station 5. So that's the remaining waiting time, and that's exactly the remaining part of the random number if we count down, and I have to store. So now it was not my turn, station 1 and station 5. Station 2 was successful. Not shown here are the acknowledgements, because otherwise the picture would be even more complicated. So now we are in the situation that station 2 ends sending something. Okay? We're here. Now everything starts again. Station 1 wants to send something. Okay, has to wait for diffs. Here. Station 2, no, doesn't want to send anything. Station 3, no. Station 4 also has to wait. You see, station 4 had a new packet arrival at the MAC layer. Station 4 didn't wait before, like 2 and 5, a new arrival. Station 5 also has to wait. Okay, now we wait for diffs. Now we are here. So next step, we all waited. And now the advantage of station 1, station 5 is we do not have to pick a new random number. Only station 4 has to pick a new random number here. Completely uncoordinated, a new random number. So station 1 reuses exactly the remaining back-off time. It reuses it. Station 4 picks a new random number. And station 5 also reuses the remaining part of back-off time. And then we count down again. So we count down with station 5, station 4, and station 1. What happens in this case, station 4 picked a random number which is equal to the remaining time of station 5. It's uncoordinated. Both start sending immediately. After back-off time says 0, we start sending. Not coordinated. Station 1, it's quite simple. Carrier sensing, again, bad luck. And we have a remaining time, what we use in the third term. So the problem now with station 4 and 5 is, as nothing is coordinated, we will have what is indicated here with this red arrow, a collision. That's it. How do we notice collisions? No acknowledgement sent back, because there's an immediate acknowledgement, as we will see on the next slide. So no acknowledgement sent back, collision. We cannot do anything against this because it's not coordinated. No one coordinates these random numbers. So you can imagine if we have smaller intervals, this might happen quite often. And this is why we increase the size of the interval if we experience collisions. That means missing acknowledgements, just to decrease the chance for collisions. But it's a statistical scheme, also a statistical fairness. It's not a guaranteed fairness, it's not a guaranteed scheme. So, okay, now we had a collision there. We will not get back any acknowledgement. What happens now? Well, station 4 and 5 both were not successful. That means but they still want to send something. They have to wait for diffs, the same station 1 has and station 5 has. But now the big difference is station 1 can reuse the old back-off time. Station 4 and 5 have to pick a new random number. They cannot reuse anything. They cannot benefit from the fact that they already tried 17 times to send something. No, if they experience a collision, this is handled exactly the same way as a new data packet. So they again have to pick a random number. And station 1 can reuse the old number. If we now picked a random number that's smaller than the random number of station 1, then station 4 can send, is the winner. But in this example now they pick larger random numbers. Station 1 finally can send, so statistical fairness, and 4 and 5 have residual back-off time, and then it's the next one. Although they still want to send the same packet on the MAC layer. After a collision, you start with a new random number. Why? Because the collision will trigger the doubling of the random number interval. That was exactly the idea. Oh, collisions, oh, that means many other stations, oh, that means doubling of the interval. So now, if you wonder why sometimes it takes so long before something answers, etc., remember the scheme. If there are more and more and more stations sending something, it takes more and more time before you can actually access anything. So this scheme you should fully understand, because this figure, because this quite nicely shows the behavior of the medium access control of a wireless LAN. And this behavior is independent of the fact what type of physical layer you use and the data rate, etc., etc. That's the MAC layer. And the MAC layer is independent of the physical layer. So, and this is why it sometimes takes some time before you can send something, before you receive something. That's also a reason why you really have to buffer a video stream when you receive something over a wireless LAN. So it sometimes can take a little bit longer. And this is also a reason why you cannot use a wireless LAN for a game controller, for example. With this behavior, there are no guarantees in latency. It depends on all the other stations. And this, by the way, is one of the reasons we cannot use wireless transmission to our video projectors. They could all receive the picture via wireless LAN, but we tried this exactly in this lecture, and as soon as some of you started surfing the web, no more connection to the projector. So in really crowded scenarios, try this Apple TV, whatever things, and all these Miracast and all these things promoted as wireless projection and wireless transmission of your presentation to the projectors. Forget it. Not in crowded scenarios, unless you have mechanisms for priorities. Yeah?
Why don't we have mechanisms for priority?
Why don't we have mechanisms for priority?
Yeah, really.
Here, yes, we could set up these mechanisms, but then you need the support in all the devices. Do we have this? No. No. So, there is no, there is some support, but not really for these purposes. So yes, you could give a PowerPoint presentation, but not a movie, for example. It's a nightmare. And if you have other networks around, how can you guarantee that they use priorities? It's not coordinated. So in real life, we tried this several times. We have all these devices, but it's a nightmare. Yeah.
What happens exactly during this? Is some kind of data transfer?
No. So the question was, what happens during diffs? If there's any transfer during diffs, all the stations have to, because they permanently send the carrier, they have to wait. So if there's, let's say, good question, very good question. So let's say here someone sends a more important packet, as I told you, a packet after a waiting time of CIFS. You're allowed to send this more important packet. Then the diffs has to start exactly after this packet. So there must be always a waiting time of diffs, a DCF interframe space, after the last time the medium has been busy. So you cannot simply say, I only wait for diffs after the last sending of user data. No, no, no. Diffs starts after the last microsecond the medium was busy. And if someone sends some more important data, like in this example for an acknowledgement, then we have to shift this whole picture for this time. So waiting for diffs then starts at the end of sending this acknowledgement. So you always perform this clear channel assessment, so the carrier sensing. So you listen to the medium, and as soon as you hear something, while still waiting for diffs in this example, you will say, okay, bad luck. Then you wait until the medium is free again, then you start again counting down these diffs. You must not reuse some remaining waiting time, something like this. No, you have to start again with diffs, and all the devices have to do this. So yes, it's absolutely right. In a real scenario, we would always hear, in addition, acknowledgements, as we'll see on the next slide, shifting this, but then the picture is even more complicated. So in a real scenario, we would have acknowledgements after CIFS, and then we have to shift everything. Because diffs, waiting for diffs really means the medium has to be free for this diffs. So medium really has to be free. The duration of diffs, you can read in the standard, depends on data rates, etc. Also how you start sending depends on if there are some legacy devices and you detect legacy devices, etc., etc. But good question, yes, you have to shift everything. If someone sends, you have to wait, because the real unicast sending is a little slightly more complicated compared to this picture. Here I showed only basically this competition between the stations. I did not show acknowledgements, I did not show priorities, I did not show beacons. I will introduce beacons, that means broadcasting the identification of the wireless LAN, etc. So now basically back to the very single transmission of a data frame. Final slide for today, because this is really something I want you to understand, because that's the core of the function of wireless LANs, and everything else is add-on, option, etc. Unicast packets, that's what you normally send from your laptop to the access point, or from the access point to your laptop. Exactly the same. Again, no special role of the access point. So this is why this is called a station. The station has to wait for diffs. And that's exactly what I explained a second ago, that as soon as you hear something in between, well, you have to wait for diffs after the end of this whatever MAC packet. So now let's assume everything is okay after diffs, and there was no load, no competing stations, nothing. Then you can immediately send. That's nice. Then you send your data. There is a maximum packet size, so you cannot occupy the medium for too long. There's a maximum packet size. And now we see exactly what happens. You as a sender, you have a physical sender address and you have a physical receiver address. Oh, don't we have MAC addresses? I will explain this next time. For the acknowledgement, we need really the layer 2 address of the physical sender of data. So you send your data, someone receives this, and after waiting of only this CIFS, this short interframe space, you immediately send back an acknowledgement. There should be no collision in this second. Why? Because a unicast packet clearly goes from one sender to one receiver. And if you want to send data, so let's say some other station wants to send something, this other station has to wait for diffs, but will receive the acknowledgement and then say, oh, tough luck, it was not me this time, and then you have to restart. After the acknowledgement packet as shown here, you restart waiting for diffs. So CIFS is shorter compared to diffs, and this is the reason why the receiver of this packet can immediately send back an acknowledgement. And in wireless LAN, the receivers always send back an acknowledgement for unicast packets, not for broadcast. Broadcast doesn't make sense to send back. After the acknowledgement, well, there's again the diffs, and then there might be a contention if there are several stations, then some data. That's the idea. So immediate acknowledgement. This acknowledgement is sent by the physical receiver of the data. Why is there a difference? Well, assume this is your smartphone, this is the access point, and this is another tablet, and you want to send data to this packet. This is all a layer 2 technology. So the source MAC address is that's the source MAC address. The destination MAC address is the destination here, the other tablet. That's the destination MAC address. But the wireless link is between your smartphone and the access point. But the access point should be transparent. Like every switch, do you see a switch in a switch network? No, you don't see the switch. But here, the MAC address of the access point is important because the access point will send back the acknowledgement. The same when now the access point sends data to this tablet, the tablet will send back the acknowledgement. So we will see next time on an extra slide that we need up to 4 addresses. The logical MAC address sender, logical MAC address destination, and then the physical MAC address sender and physical MAC address destination, which can be the same, but in this scenario you see the logical address are the MAC addresses of the sender and of the receiver. The access point should be transparent, but the MAC layer requires an acknowledgement, but from the physical receiver, because this is the one checking the checksum, because the wireless medium has the problem, not layer 2 end-to-end, but here the wireless medium. This is the reason why we will have 4 addresses, as I will explain next time in more details. Also shown here, I just explained this because of this acknowledgement. Also shown here, the growth, this doubling of our window where we pick our random number from. So that's the contention window, and as soon as I do not receive an acknowledgement, I double my window. And if I receive acknowledgements again, I can halve the windows again. So that is the idea. Initial attempt, the window is between 0 and 7. First retransmission, it's up to 15. It's the first, second retransmission, it's 31, third retransmission, 63, fourth, etc., up to 55. We stay there, and after a certain amount of retransmissions, we say stop, medium doesn't work anymore, and signal this to the higher layers. That's the basic idea, that's the basic medium access method. Please do look into this, and please try to understand these mechanisms, because then now we put all the other things on top of this. The other things are not that important, how this and that is done, but the basic mechanisms, it's so different from this controlled system like GSM and from this very controlled system like Bluetooth, where we have masters and slaves. Okay, that was a lot for today, not many slides, but a little bit more content. So now enjoy this perfect summertime and see you next week. Thanks a lot. Okay, good morning and welcome back to Mobile Communications. The last time I introduced the basics of wireless LANs, I took a little bit more time on explaining medium access. Why? Because this is really different when comparing it with mobile communication systems, classical mobile communication systems, where you have the base station really controlling the medium access. And here, for these distributed wireless LAN systems, the decision was made to say, okay, we do not want to have a central base station controlling all the access, but more or less all the devices compete for medium access. And that was special, this system. But I also explained that without any central control, it's quite difficult to guarantee any quality of service. But as we also know it from wired LAN systems, we use best effort. Why? Because most of the traffic we put on top is IP-based. IP does not really give you guaranteed quality of service. So why really put a lot of effort into quality of service in the lower layers if you do not really use it for the higher layers? Okay, so, and we stopped when I explained the normal unicast scenario. Unicast, that means you send a packet after this waiting time, diffs, after maybe a contention window, and then the receiver immediately sends back an acknowledgement. I also explained that in cases of interference, remember the keywords were hidden exposed terminals, an option is to use RTS, CTS. RTS and CTS are special packets, as I will show you. And the basic idea there is that first of all, again, you have to wait for diffs before sending RTS. Why? Well, the first initial packet is treated like any normal data packet. So this means you have to wait for this diffs, the DCF, distributed coordination function, interframe space, diffs. Okay, so you wait after diffs, if, for example, the medium was empty. And for this RTS, the same applies as for normal data packets, like waiting for diffs, like contention, window, etc., etc. But now the special thing is that we wait only for short interframe space before we send back the CTS, the clear to send. And if you look back in the chapter about MACA, this median access scheme with collision avoidance, there we had the CTS and RTS scheme that tries to avoid the problem of hidden and exposed terminals. And this is exactly what you can apply here for wireless LANs. So after the RTS, you can send, after a short waiting time, your CTS. And after the CTS, again, only a short waiting time. And then you can send your data without any contention window, etc. So that is the basic idea. Why? Again, because this helps to avoid the problems of hidden and exposed terminals. That was the problem, that you cannot hear other terminals and two terminals try to send to the same receiver, and then you have the collision at the receiver, but you do not hear this collision. So that's the idea of RTS and CTS, and you see there cannot be any additional collision because you only wait for a short interframe space and not for a long interframe space. That was the idea, as long as there's no station moving into the transmission range, etc. And how do the other stations actually know from this? Well, as soon as you receive an RTS, you set something that's called the network allocation vector. So that means internally you set a parameter that tells you how long will the medium be blocked. So the network allocation vector tells you, okay, now the medium will be blocked for this and that microseconds. And during that time, I'm not allowed to access the medium. If I receive something or not, whatever carrier sensing tells me, I know exactly, okay, I'm not allowed to access the medium. And the same is true for CTS. This also sets the network allocation vector, maybe in another set of stations, because if you remember, this could be different sets of station. We had this station A, B, C, that was the scenario where A and C wanted to send something to B, and now the problem is that we might have a collision here at B, and A and C, they cannot see each other, so they are hidden from each other. That was our hidden terminal problem. But now if we use this RTS and CTS scheme, we set this network allocation vector in all the terminals receiving RTS and CTS. That means they will not try to access the medium if they receive something or not. After data, we immediately send back the acknowledgement, and then, well, you can start over again and everyone can compete for accessing the medium. This scheme can be applied, this is optional, and if you look at the scheme, it fits perfectly also into the other scheme, because not all the stations have to follow it. So it's mandatory, if you look at the standard, only to use the network allocation vector, but it's optional to use RTS, CTS. So as soon as you receive RTS or CTS packets, you have to set the network allocation vector and you have to follow the rules. That means not to access the medium during this time. But you do not have to use the RTS, CTS scheme. So your station can decide, now there's too much interference, maybe due to hidden terminals, then I switch to RTS, CTS. Other stations may stay with the classical scheme or may also switch to RTS, CTS. That's completely independent. It's a distributed system. No one controls the scenario. So that is the idea of RTS, CTS. But as you can clearly see, the problem of this scheme is you have additional waiting time. Here you see this is additional waiting time, sending RTS, waiting for CIFS, sending CTS, waiting for CIFS. Without this, you only have to wait for diffs and then you can send your data. But here you have additional waiting time, and it's worth doing this only if you experience, well, certain level of interference. And the system thinks that this is due to hidden stations. So that's the idea. So you see this is one option implemented. There are some additional options implemented. For example, fragmentation. If you want to send more data, that's one of the problems you have. If you look at an IP packet or if you look at packets transmitted via Ethernet, we all know 1500 bytes. 1500 bytes sending over the air is quite dangerous because you have a certain high bit error rate, and if you have more or less equal distribution of the bit errors, this hurts much more 1500 bytes packets compared to 100 bytes packets. Just statistics. So it's wise to perform certain fragmentation. And typically wireless systems, they are able to transport only smaller packets, 100 bytes, 200 bytes, but not 1500 bytes. And so, but at the same time, you do not want to compete for the medium all the time. And this is why wireless LANs can, for example, perform this again optional fragmentation, so that you split your original larger packet into smaller fragments, and you can send after you can successfully access the medium, you can send all your fragments, but here you only have to wait for CIFS. So you only have this short waiting time. So after accessing the medium, so wait for diffs, RTS, CTS, and then you can wait for CIFS, send a fragment, get the acknowledgement, wait for CIFS, send a fragment, get the acknowledgement. So this is then much faster. So that's one of the ideas. But if you lose one of the fragments, etc., you have to perform retransmission, etc., etc. So fragmentation is an option. So you see, there's this standard scheme used for, I would say, 99% of the transmissions, but then there are some options, and they have to fit into this distributed scheme, because you don't know what the other stations do. They only follow these basic rules of waiting for a certain time, using network allocation vectors, but you do not have to use fragmentation, do not have to use RTS, CTS. These are options. If they are useful or not, well, for example, RTS, CTS is really considered a big problem if you have voice over IP over wireless LANs, because you insert an extra delay by using RTS, CTS. Without this, yes, you may lose more packets, but then in the end, you can show that, especially for voice transmissions, it might be better to lose some packets, but to avoid this additional delay. So depending on the application, it might be good not to use RTS, CTS, although you might have problems with hidden stations, because they are statistically distributed also the excess, so you will lose some packets, but it's better to lose some packets than to have the additional delay all the time. So there's not the single solution that is best for all applications. So many more options, that's not the important part. And now, similar to the physical layer, we have a certain frame format. And this is now a MAC frame, full-featured MAC frame. This is not the frame you always have to transmit. This makes it a little bit more complicated compared to, for example, Ethernet frame, where I say, okay, this is the Ethernet frame, and this is the frame I always use. Here, as you see, only the first three and the last field are present in all frames. So we always have a frame check sequence, and we always have frame control, duration, and at least one address. So yes, you need at least one address to address something. It's nicer to have some more addresses depending on the setting. So we have different types of frames. You see, within the frame control, there's, for example, a type field, like the control frames or data frames. Control frames like acknowledgements, where you only wait for SIFs, or data frames, normal data frames. We have sequence numbering, because we might lose some frames, many more fields. And the interesting part is now, we have many more address fields, address 1, address 2, address 3, address 4. Why do we have so many addresses? This is one thing we'll look at now. So the MAC frame format is more complicated compared to classical Ethernet formats. Again, like I always say, you don't have to learn frame formats and things like this. You have to understand the basic ideas, but not to learn fields and 6 bytes for this and that and whatever. So here we have the classical 6-byte MAC addresses. MAC address 48 bits, 6 bytes. So that is what we know from Ethernet. All Ethernet adapters, they have a MAC address. That's simple. So for the normal Ethernet frame, we have a sender and a receiver address. That's quite obvious. So if you have a switched Ethernet network, the sender address is the MAC address of your Ethernet adapter. The receiver address is the MAC address of the Ethernet adapter of the receiver, not of the switch. Switches are transparent. You will not see the switch in between. We have transparent switching in Ethernet. You remember maybe from telematics, transparent switching, 48-port switch. You will not see the switch. Switches are invisible. We have a star topology with the invisible, so to say, switch in the middle. So the sender is the physical sender, your PC sending something via a switch to another computer. Here it's different. We have 4 addresses. Why? I will explain. And we have some more fields indicating, do we send data to distribution system from a distribution system? And some more fields. So, why is it more complicated? Think of the normal system in a wired scenario. We have a PC sending something via a switch to another device. And so we have a source address and we have a destination address. And these addresses, they are the logical source and the logical destination, as well as the physical source and the physical destination. There's no difference between these types of sources and destinations. Here, it's different. Why? You have your wireless device with your antenna, and you have a distribution system. That might be as well only a switch, but the standard says it's a distribution system. Now, let's put it quite similar, and you have your wireless device with the antenna here. So, now what is the difference? Well, we also have a source address. This is my source, and this is my destination. We are operating on layer 2. Remember, layer 2. We are not on IP layer. Layer 2. So, if I have a switched Ethernet, I have a source and a destination. The same is true here. I have a source and a destination. But the big difference now is, if we send a packet, we get back an immediate acknowledgement. This acknowledgement is not sent by the destination, but here, by the physical receiver. And this is why we have a source address, which in our case equals the transmitter sending something, and we have in between a physical receiver. On layer 2, this receiver has also receiver address, a valid MAC address. And now suddenly, for the acknowledgement scheme, the switch, so to speak, the distribution system, at least the access point, is visible. Not visible to you on layer 2, but needed for the acknowledgement scheme, because the acknowledgement in wireless LANs is not an acknowledgement from the logical destination. Also in switched Ethernet, we do not have any acknowledgements, because we use typically unacknowledged best effort transport on layer 2 from a source MAC address to a destination MAC address. There is no acknowledgement in Ethernet, not at all. So this is left for higher layers. Transport layer, TCP for example. Not IP, not UDP. So source address, destination address in wired systems, no acknowledgement. But here in wireless systems, due to this way higher bit error rate, we need an acknowledgement. Because if something happens, layer 2 already here tries to retransmit. But this acknowledgement needs a receiver address and a sender address. So you know this acknowledgement from this adapter to that adapter. And this is why in such a scenario we need additional addresses. So for example, we have a situation where, this is the third line here, that's exactly this scenario, where we send data to an access point. And there's a bit indicating in each packet. Now this is a frame to the distribution system. The standard doesn't tell you anything what the distribution system is. Here it looks like something like a switch. So if we send a packet over the air from our device to the distribution system, that's exactly the case shown here, where we say send a packet to the destination system. And then we use our addresses as follows. You see, in this case, we need 3 addresses. Why? Well, one of the addresses, let's start here, is the logical destination address. That's the destination address of our logical receiver. That's a destination address. Then, address 2, that's our source address, the logical source address. But in our case here, as you see, acting also as physical transmitter. So our source address, the logical source address, and the destination address here, the source address is equal to our physical transmitter of this packet. And this is then the receiver for this immediate acknowledgement. This is why, we need another address. And now why this third address? The third address basically is our receiver of the packet over the air. this is something we never used in normal switched fixed Ethernet. No, but here, due to the fact we need this acknowledgement, we address the receiver. That's a MAC address, the MAC address, and that's basically the identification of my system. So we have the SSID, the identification, and here this is my address 1, that's the receiver in this case. But that's only for the case I send something to the access point. So that was one of the scenarios. And then you see there's also a scenario the other way around that we say, okay, if, for example, now my access point sends something to my device, then we have, as you see here, from access point, we see, well, we use the 3 addresses in a different way. We still have logical destination address, logical source addresses, but now we also need the address of the access point, because it might be the case that the logical receiver, which is also the physical receiver in this case, does not receive the packet or receives the packet. This is again needed for the acknowledgement mechanism. So these 2 are the cases where we need 3 addresses. Then there's a case for ad hoc networks where we basically use it a little bit different. Ad hoc only sending point to point. And the, so to say, most complex case is the 4th one, where we need all 4 addresses. Why? This is the case when we have a packet, that's case 4, a packet in flight within the system, inside a mesh system, inside the distribution system. If you're inside the mesh, we still have the logical sender and the logical receiver somewhere. But if I'm a packet somewhere in between, I also might have 2 completely different physical senders and physical receivers. And this is where we need our acknowledgement mechanism. It's not end-to-end, and everything is on layer 2. So this is the special case where we need 4 addresses. We have our, as you see at the end, we have our logical, these are the logical addresses we need, otherwise we will not find the destination. And then in addition, we have this physical transmitter address and receiver address. This is needed for this hop by hop forwarding of a packet or by forwarding in the distribution system. So this is just one example that shows you, okay, that's really different from this simple switched Ethernet scenario, where we do not really see the switch. Just a remark, this does not mean that you cannot access your switch. Yes, sure, the switch also has MAC addresses, IP addresses, a web server or whatever built in. But for the normal function of the switch, you don't want to see it. There's no acknowledgement mechanism, nothing. You do not really see the switch. There are some certain cases, but normally you do not see anything from the switch. So this is why we need more than only the 2 addresses you have in the normal Ethernet. Okay, and that was just one example. Then if you look at the packet, you see some quality things, power management, whatever, some additional features you might need for wireless transmission, power adjustment, etc. Okay, then that's just something to look up. There are special frames like, okay, why is it worth doing RTS, CTS? Yes, because the packets are much, much smaller. If you look at the CTS, it's 448.812.0. That's only 20 bytes. And the CTS is only 14 bytes. And this is why it might be worth doing RTS, CTS, because you send 20 bytes, the chance for collision are quite small. There might be collisions, RTS packets. They could collide, or RTS packet with whatever packet could collide. But if you're successful after RTS, waiting for CIFS, CTS, waiting for CIFS, then you can send your longer data packet. That was the idea. And special acknowledgement packets. And they all contain this important field duration, and this field sets our network allocation vector. So while sending the RTS, everyone receiving the RTS knows by reading the duration field, now I have to remain quiet for the next whatever microseconds. So that's the idea. So the duration field sets the network allocation vector. That's the key idea. Okay, so Then we have some more management functions in the wireless LANs, because if you switch on your device, you try to find the local area network and you try to stay within the network. Yeah, we have power management functions because we want to sleep most of the time. We have some functions for association, reassociation, so you have to integrate yourself into a network. So you have to manage roaming between networks, scanning for networks. We have a management information base, as I explained in telematics for this before. We have many more functions needed for reassociation, association. So for example, we have beacons. All the base stations, they usually, and this is one of the differences to other devices, they send out beacons every 20 milliseconds, every second, depends on the configuration. You send out a beacon with a timestamp. Why is this important? The beacon not only tries to synchronize devices a little bit, but the beacon frame also contains some more information, as I will explain. Among others, the ID of the network, so the name, the SSID, that's important, so that your device sees, oh, these are the networks I see. And this is sometimes why it might take some time before you receive all the names, the IDs of the network, because it might happen that you are not allowed to send the beacon. You see, there are no special rights for the base station. No special rights, so if the medium is busy, you have to delay sending out the beacon, but then you can also put another timestamp in the beacon. This is quite important, the beacons also for the sleep-wake patterns of the devices, as I will show. This is also true for ad hoc networks, but that's not main focus here, so we focus on. So why do we need this? Because power is one of the main problems of the devices. So wireless LANs consume power, energy. Well, consuming, you cannot really consume energy, but so they drain the battery. And so the key idea is switch off the transceiver if not needed. So the station tries to stay asleep for most of the time and tries to wake up in the right moment. Yeah, but that's a problem. So when to wake up, and this is where you need the synchronization. So if I know that every second I might get some important information, then I can sleep, wake up every second, listen, is there something for me? If not, sleep again. That's the idea. This is why you need some timing synchronization. And during these beacons, or right after the beacon, we can, for example, transmit a so-called traffic indication map. That's one of the methods used. And in this map, you have a list of receivers the base station has data for. So if you send something to a wireless device, the base station can buffer it. And after the second, it can send a list of receivers to all the receivers and hopes that they are awake. And if you see yourself in the list, you stay awake. If not, you can fall asleep again. That's the idea. So you wake up, check the list. If not, fall asleep again. Wake up, check the list. Oh, it's me. You stay awake. And then data transfer starts. So that's one of the ideas. And the same exists for broadcast and multicast. So not only for unicast, but also for broadcast, multicast, because there might be multicast, broadcast data. Think of ARP requests, something like this. And something similar exists for ad hoc, but that's not very efficient. And there are papers showing that this does not scale. There are some new mechanisms. If you're interested in these details, it's called APSD, Automatic Power Safe Delivery. So new methods that are now being used, replacing these classical schemes. But the basic idea is always the same. You have to indicate to potentially sleeping devices that there's something interesting for the devices. If they stay awake all the time, they waste energy. If they sleep too long, well, you increase the delay while sending. Well, you wait. Oh, now it's awake. Now I can send something. So that's one of the problems. So just to show you one of the ideas that basically you send periodically, and this is why you need the synchronization. You send these traffic indication maps. That's one of the ideas. And all the stations, they try to sleep, wake up, they check the traffic indication map, not for me, they sleep again. And if they check, there's something for me, then they can send back information telling the base station access point, in this case, I'm awake, I'm there, and then data transfer can start, you can send some data. So that's the basic idea. I will not go into the details because we have now more advanced schemes with these 11E standards. But still, it's still a basic idea that you try to keep the station sleeping most of the time, and you have these periodic wake-ups. Periodic wake-ups might be a problem again while using, for example, continuous voice communication, because there are even cases where you can hear this, that the station sleeps and then you get this kind of staccato voice while talking. So it's not always a good idea. So there's the same for ad hoc. Important. Interesting for the everyday use is the roaming feature. If you have no connection, if you have bad connection, there are two things you can do. One is you can scan the environment. So you can passively listen into the medium for the beacon signals. The other thing is you can send probes into the medium and wait for an answer. And this is what most of the devices do. Why? Because it's faster. Instead of waiting, you send a probe, and what you usually do is your devices, they know these are the last wireless LANs, SSIDs I've seen. I check them if they're available. If yes, you can reassociate to the network. If not, this might be still faster compared to just waiting for the beacons. The problem is this is exactly the way how we can find out where you've been. Why? Because your device will tell, oh, this is the Starbucks SSID, this is this BT open zone, this is that. So your devices tell the whole environment where you've been, basically in which wireless LANs you've been, the SSIDs. So that's quite interesting. So from time to time, you should clear this list, because otherwise most of the devices simply tell everyone at least which wireless LANs you have seen. Okay, so sending probes, yes. And then you start this reassociation, you start requesting the access point, am I allowed to participate? And this response can be a success, and then you can participate on layer 2, or it's a failure, you're not allowed, etc., etc. So that's the idea, and as soon you're accepted, the access point can then act, for example, tell the distribution system that you are there. Why? Because if you associate to the network, the access point knows your MAC address, which is important for the distribution system, however it looks, because the distribution system can then reroute traffic to this access point. If the distribution system, for example, a switch, has a list of MAC addresses and associated ports, the switch has to learn. Now you're with this port and not with the old one. Because otherwise roaming doesn't work. So the system has to know where you are, at least where your MAC address is. So to reroute the traffic. And if the system is friendly, it can tell the old access point to release resources maybe, but otherwise you have a refresh in the tables. And if you do not use the system for a certain time, 2 minutes, for example, you will be deleted anyway in this cache. This system for roaming is pretty slow, not really high performance. It will not work, for example, for vehicle to roadside networks. This is why there are special standards for faster roaming. Or, for example, in networks like we have, we do not use these systems. So these are more or less, I would say, proprietary systems. We do not have full-featured access points, but access points that basically translate wireless into wired packets. And then we have a concentrator here at the compute center, and there we perform all this roaming, load balancing, checking for free open frequencies, etc., etc. We can also locate, for example, interference, sources of interference. So if you start your own network here on the campus, we can locate the location where you start the networks. This is important to see if we have certain spots where we have higher interference, etc., etc. So these access points, they do a permanent scanning of the frequencies, to see which frequencies to use to perform certain load balancing, etc. Because more than 1800 access points you have to manage somehow in an automatic way. So these are the standards, and then the real implementation is sometimes a little bit different. And as you see, the original standards are not fast enough for real-life scenarios. This is why I will also not focus on this. It's just you should have heard of it, how this works in principle. And so you see, important, the basic mechanisms, and then many options. And the current developments, so already a year ago, I will show you the new standards soon, showed, well, we have many more enhancements like quality of service. That does not mean that all the devices already follow this. So especially for quality of service, for example, for telephones using voice over IP, over wireless LANs, we need some quality of service. We have standards for higher data rates. I explained this a little bit. OFDM, enhanced security mechanisms, and so many more standards. And even higher data rates, and you see that's quite a lot. Faster handover. And so 2012 was the time when IEEE said, okay, let's put together the major new add-ons and create a new standard. So the official 802.11 2012 standard now comprises many of these add-ons, of these newer standards, higher data rates, more security, etc. Almost 3,000 pages. So it started out with a very thin standard, and now it's bigger and bigger again because we have so many options. But these are not the newest standards. You see, we have the mesh networking included. That's always when I said, okay, we have these three topologies: infrastructure, ad hoc, and mesh. So this is a self-configuring wireless distribution system. So that's quite interesting. If you have mesh networks in between, it should configure itself automatically, compared to the classical ad hoc mode where you could only send point to point. Now we have a mesh network in between. But this is all on layer 2. And many more, and one of the more important standard is 11AC. That says very high throughput with lower than 6 gigahertz. And the goal was almost 7 gigabit per second. So operating at 5 gigahertz. 7 gigabit per second, 5 gigahertz is the band where they operate on. There are some more standards operating at 60 gigahertz, and etc. etc. There are some working groups working on next generation positioning, etc. If you're interested in this, here you have the links. And many of these add-ons will never end in products. And sometimes you see things already in products that are not really a standard. Okay, that's life. So 11AC is now, this is why it's in bold phase, it's an important standard because we have the products for it. Okay, so that's currently the upper limit for 802.11 devices. So single link throughput more than 500 megabit per second. That is quite good. And this is only a 5 gigahertz standard, not for 2.4. For 2.4 gigahertz, use 11N. There is no AC for 2.4 gigahertz because we need more bandwidth, more of the spectrum. You see, up to 160 megahertz, at least 80 megahertz. 80 megahertz, that would be almost the complete 2.4 ISM band. So 80 megahertz, 8-time MIMO. So that means you need many more antennas, different modulation scheme, 256 QAM, beamforming, space division multiplexes, so you can follow devices in your apartment. Your base station can follow single devices. And then we have configurations, for example, as shown here. We have the access point here with typically many more antennas, visible or not visible. And so we can have big data stream to the TV set, a thinner one to a tablet, and very thin ones to some smartphones, whatever. And offering different data rates to different devices by allocating different antennas to the devices, for example. Then we have whatever, almost 7 gigabit per second for the complete access point, which is almost 5 gigabit as real throughput. Remember, we have still waiting times and this and this and this, and then allocating some other data rates to other devices. Many of the protocols fields had to be redefined, some other procedures, and now we have also some more simplifications, at the same time some new procedures. So that's always the case that you think, okay, what are the options we never used, so let's get rid of it, but oh, we need some more options. So, and you try to keep the balance, so not to make the standard even more complex. That's one of the problems. The interesting thing is now, and this is one thing I want to show you, how your new devices following 11AC now allocate spectrum. They use RTS-CTS in a fancy way. So the example here shows how you use RTS-CTS. So we have an RTS first, and then followed by CTS, followed by data, followed by acknowledgement. Well, a little bit different names, so it's not that easy to read. So RTS, CTS, data transmission, acknowledgement. Why? Well, the point is that shown here, frequency on the y-axis, time on the x-axis. Shown here is we send 4 times, 1, 2, 3, 4 times an RTS on different bands. We have here 20 megahertz, 20, 20, 20, 4 times 20 megahertz. And we send on all these 20 megahertz bands, we send a RTS. And then the recipient reports back with a CTS that everything is fine. Why 4 times an RTS? Why not 1 RTS over everything? I will show the next example. But so in an ideal case, we probe 4 times 20 megahertz. And if we receive the CTS perfect, then we can use for our data the full 80 megahertz, which is nice, because with full 80 megahertz we can transfer a lot of data and we will get back acknowledgement. No interference, success. That's the ideal case. Why do we split this up? Because there might be some nearby access point that uses another channel as a so-called primary channel. And it could happen, and this is shown in the next example, that we probe again with an RTS 4 times 20 megahertz. We try to get 80 megahertz, but now there is a nearby access point of your neighbor, for example, using here a certain part of the spectrum and creating some interference. So we might have now a hidden exposed terminal problem, now even on different bands, because there might be a neighbor using some of the bands. The result is you will only get 2 CTSs back. That means you can only use 40 megahertz of the spectrum transmitting your data. So you see, we have here a quite clever scheme of using RTS-CTS, checking in parallel chunks of 20 megahertz, trying to get full 80 megahertz, or if it's extended, even 160 megahertz, to transmit a lot of data. If not, then at least 40 megahertz. So this is how you integrate this new standard, 11AC, into the already existing standards, because at 5 gigahertz we already have the 11A standard operating there, offering maybe 54 megabit per second using 20 megahertz. So you cannot simply say, oh, this is a green open field, I will ignore all my neighbors, I will simply transmit at 80 megahertz. This would cause a lot of interference for everyone. Plus, your neighbors will destroy part of your data. That's not good. So it's better first to check for these 420 megahertz bands, and if a part of it is free, use this part. Otherwise, you can use everything, etc. So that's a special feature of the new 11AC devices. So most of the new devices you buy, they follow the 11AC standard, and you have a tremendous gain in performance. It's really extremely fast. So no one of you, I guess, has a DSL or whatever access that comes close to these data rates you can achieve here. So 200, 300 megabit per second is achievable. This even comes close to what you have if you have a switched Ethernet at home, because what can you have there? Usually a 1 gigabit link, but then this already hits, well, the maximum performance of your NAS, for example. So a classical NAS, independent of the vendor, at least we can afford, then has something like 400 megabit per second, 500, but that's it if you have a RAID 5 NAS, etc. But you will not have normally a NAS with really high data rates. Yep.
The trade-offs again, interference or?
The problem is the interference, yes. So we achieve, the trade-off is always, we achieve the high data rates only because we can use more of the spectrum. And the hope is, as long as not too many use 11AC, the hope is, due to this bursty traffic, that we can basically squeeze into gaps. That's the idea. Sure, if someone of your neighbors uses 80 megahertz all the time for 4K, 8K movie transmission from your special NAS station, if it supports these high data rates, okay, to your device, there are some stations that can support this right now, then you're lost. Yeah, that's a problem. Okay, but we cannot do anything against this. So all these wireless LAN technologies only work if there are enough gaps, so statistically, but not if someone really downloads a huge amount of data. And if we all go now to 4K movies, that will be really interesting, because this loads a normal network completely. Well, no chance. So even if you have a gigabit switched Ethernet, it will be funny with 4K or 8K movies and 3D 60 frames per second. Interesting, at least for wireless, not now. But this will be where it goes. Yes, in the future, definitely yes, it will be interesting. Okay, so that was basically all I wanted to say about this kind of high performance and more and more multi-gigabit, but also a lot of energy. Sure. And now we come to a complete different approach, also operating at 2.4 gigahertz. An approach that basically said, well, can't we, and that was 20 years ago, can't we replace cables? Cables between the headset and the device. That's exactly what I'm using right now. A headset, whatever device, small, simple device. I want to be able to operate it for hours or days. Use it for, speaking, 12 hours, 16 hours, without any problems, without charging any batteries. Can I replace a cable? Because handling cables, that's cumbersome. And I bet you have seen even headsets for both ears without any cables, and they all use today Bluetooth as a technology. One of wireless LAN, it's energy. It's one point. The second point is quality of service. So Bluetooth as a technology, that is basically a cable replacement and a replacement for infrared. I already told you that 20 years ago, we also had infrared connection between mobile phones, for example. And the next goal already at that time, 20 years ago, was maximum €5 per device. Euro. We didn't have the euro at that time, but well, $5, something like this. So, okay. At the same time, short range. Short range, 1 meter, 5 meters, that's it. 10 meters, maybe. License-free ISM. Not that crowded at that time. Important, voice and data. Low data rate, relatively low. Voice, yeah, voice requires, let's say, 64 kilobit per second. That's already good quality. That was the idea. And one of the first modules seen here, the idea was some kind of a connection between a mobile phone and whatever there was, a printer, a camera, things like this. So, different idea, not a replacement of the local area network. So history, quite short, basically 94, you see this is why I mean 20 years ago, more than 20 years ago, there was the MC Link project at Ericsson, and basically, so how to replace the cables. And during a visit at his friend in, I think it was somewhere in the US, they discussed about names, about new projects, etc. And they came up with a name according to an old king in Denmark, 10th century, Harald Blåtand. And if you directly translate this name without knowing the real meaning, then you could come to, if you use modern Swedish, could translate this to blue, and tand to tooth. But blå at that time also meant dark. So no one believes that someone had blue teeth. I'm sure. But so Blåland, for example, is Africa, the dark country. So Blåtand, that's rather means someone had dark complexion, so maybe dark hair, etc., which was not normal in the Nordic countries. Okay, that's for the history. So, so Bluetooth. Then it also started with, as a symbol, the Viking sails sailing into whatever the future. Today it looks a little bit different. A special interest group was founded with many members. Pretty fast with commercialization. Already 2005, so 10 years later, 5 million chips per week. And today you will find Bluetooth in basically all devices. It's integrated. And usually the Bluetooth chips, they come together with FM receiver, radio receiver, and some more features. So that's nothing special. So you will find the slide some more funny facts about history. And so they erected a runestone there at Ericsson in memory of this Harald Blåtand. But, well, sure, this is not the original runestone. And it says that it's in memory of this Harald Blåtand, who gave his name for this new technology for wireless mobile communication system. So, okay. The original runestone looks a little bit different. So at least a little bit history here in mobile communication. You can look this up. So no one had blue teeth. What is the idea behind this? 2.4 gigahertz. But now we split this into 79 channels and we perform frequency hopping. A slow hopping scheme with 1600 hops per second. Slow hopping, why? Because we transmit many bits on one frequency, then we hop to another frequency. So this is a slow hopping scheme, 1600 hops per second. And the interesting thing is, the hopping sequence is random, derived from a master. Okay, so there's a master, as I will explain, and the master tells the devices how to hop through the frequencies. Why do we do this? Because if we have different hopping patterns, we avoid interference. Well, it might overlap, yes, but if you have different Bluetooth networks, they have different hopping patterns, and so we hop through 79 channels, and usually there's no interference. So that is one of the ideas. There's a time division duplex scheme for sending and receiving, as I will explain, and the services offered are synchronous, and that's different from wireless LAN, a synchronous connection-oriented scheme for voice with forward error correction, 64 kilobit per second, guaranteed service, and an asynchronous connectionless for data with, at that time, 700 and something kilobit per second downstream, 50 something upstream. So that was more than enough at that time, 94, 95, then to 2000 for communication. The interesting thing is now, that's completely different from wireless LANs, how you create a network. So the idea there is to form a so-called piconet. And now we really have a master. Big difference to wireless LAN. We really have a master. We have a pure ad hoc network, and one of the devices now acts as a master, creating a network within radio range. So we have a certain radio range, and the master determines the hopping pattern and the slaves have to synchronize. There must never be two masters. Only one device can be the master. Which device? Doesn't matter at all. Could be your headset, could be your smartphone, could be your printer, your camera, your laptop, tablet. Doesn't matter. So one device is the master, and if you want to participate in this piconet, you have to synchronize. Synchronizing means you have to follow the hopping pattern through the 79 channels. Only if you're synchronized and if you follow the hopping pattern, then you can communicate. Otherwise, you don't know the frequency. So you have to synchronize and follow. How? I will explain. So one unit is the master, and we can have up to 7 simultaneous slaves, never more. So Bluetooth piconets can have one master, up to 7 slaves. Maximum 8 active devices, never more. So, and if you want to participate, as I said, you have to find a master, you have to synchronize, and then you have to follow the hopping pattern. That's it. If you want to create your own network, you can say, I'm a master, and then you have to wait for a slave, and if someone follows you, you have created a piconet. But you cannot enter another piconet acting as a master. There's only one master. And if there's no master anymore in the piconet, the network doesn't exist anymore. Because then, how to derive the hopping sequence if there's no master? So you have to have a master, and you can have up to 7 slaves. You can have some more parked devices. Parked means those devices know the address of the master. They can also follow the hopping pattern, but they cannot communicate. And then there are some standby devices. So I will explain now how you create this piconet. So because this is completely different from the wireless LAN. So first of all, you have many devices here. And they're all within the radio range of each other. So that's usually not a problem. Usually no hidden terminal problem, etc. There might be these problems, but usually that's not a big problem. So first of all, one of the devices decides I will be a master. How? Well, I'm the first device being switched on, for example. Or my owner tells me, now you're the master and you're the first device, and now other devices will follow. Or, for example, simple headsets can never be master. They don't have those functions integrated because it's cheaper. Because you always know, you will always connect a headset to a more powerful device like a smartphone or tablet or whatever. So this is, you don't have to be a master. So there are also slave-only devices. So one device starts, and this master basically tells everyone a device ID, which is the MAC address. So basically the MAC address, the ID, MAC address, and its clock. And now there is a fixed algorithm how you derive the hopping pattern, so hopping through the frequencies, based on the ID and the clock. So the ID basically is the seed for the random number generator, and the clock is then the phase shift. Where are you right now in your random number sequence? And the random number sequence tells you how to jump through the frequencies. So that's the basic idea. So it's a full deterministic algorithm, and the MAC address and the clock basically tells you where you are in which random hopping pattern. So that's the idea. And as soon as one master acts, one standby device acts as a master, this device determines the clock, tells the other devices the clock, and if you're synchronized, you know the clock. So slave devices and park devices, they know the clock. So green are the slave devices, one master. Park devices, they know the clock, and they can now follow the master. Only the slave devices can, in addition, communicate. Why? Because we have only 3-bit addresses. And with 3-bit addresses, you can only address 7 slaves plus broadcast. There is no master address. The master does not need an address for communication. Why? We will see. So 3-bit active member address. Active member address 3 bits, 7 slaves, plus a broadcast. Why don't we need a master address? We will see, because slaves are only allowed to talk to the master. So if a slave sends something, we don't need a destination address, because the destination is always the master. We only need a sender address. If the master sends something to a slave and the slave receives something, we don't need a sender address, because it's always the master. We only need a receiver address. So you see, we only need one address in the packets, because the communication is only allowed master-slave. There are some special cases for slave-to-slave communication, but the normal communication is only master-to-slave. If 2 slaves want to talk to each other, they have to talk via the master. Makes the system very simple. Okay, that's the idea. We have the 3-bit active member addresses and many more 8-bit park member addresses. That's not that important right now. That's important for power saving. So you form Piconet, completely different compared to wireless LANs. So there is a special feature called a scatternet. So scatternet means kind of a scattered, distributed network. You can, based on the standard, in theory, link different Piconets basically by, for example, a slave jumping back and forth between 2 networks. What does it mean? You synchronize to one master, receive data, then you synchronize to another master, send data. You synchronize back to this master, get some data, sync back to that master, send and receive some data. So masters jumping back and forth, they could enable a so-called scatternet. That is in the standard, but basically there were some chips. Never really seen that someone uses scatternets there. To set up large networks, we usually use wireless LANs. So in the end, Bluetooth today is really a cable replacement technology, not a real networking technology, something like this. Okay, so that's just if you ever hear of scatternets. So the Pico networks, in the early days, they had an overall data rate maximum capacity of 720 kilobit per second, as we will see. So again, yes, we have a huge stack. Why? Because, for example, we have special audio applications that do not want to use all these communication protocols to avoid latency. We also have, that's history, a lot of AT modem commands integrated. We have the classical, what we used over infrared, business card exchange protocols. We also have the classical internet protocols based on serial adapters, etc., etc. So basically, in the early days, Bluetooth tried to replace infrared serial cables, so the classical technology, but also wanted to offer audio with very low latency. And so Bluetooth used, shown here in blue, classical protocols, and integrated, shown here in orange, some new protocols. New radio, new baseband layers, some managing protocols, a new service discovery protocol. Service discovery protocol is important, that's here, important for finding other Bluetooth devices. If you switch on your device, you will see sooner or later a list of other Bluetooth devices. This is where you need a service discovery protocol. Again, it's just to make the picture complete, not for learning whatever. So, interesting, again, is something, what is different to a wireless LAN? We now jump through frequencies. We stay for 625 microseconds, we stay on one frequency, FK, shown here. Now the pattern, the normal pattern is as follows. The master sends something on a frequency, then the slave can send something on another frequency. Then the master on yet another frequency, then the slave, then the master, then the slave, master, slave, master, slave, master, slave. So Bluetooth follows a very strict master-slave scheme. There's always the master using one frequency, sending a certain number of bits, then a slave, then a master and a slave. And the master can tell the slave, or can actually send data to a slave, and can allow a slave to send data. Or the master can pull slaves, ask if they have to send something. The slaves can never send data immediately, like in wireless LANs. We have no master and slave in wireless LANs. So it's basically, here we have a master and slaves, and the master controls the network. And here you can see this hopping pattern. So we hop through 79 channels. For certain reasons, we can use the same frequency for a longer time to send more data. So for example, the master can occupy a frequency fk for 3 time slots. Then we can send more data, achieve higher data rates. The same is true, for example, if the master allows it, the slave can also occupy for 3 or for 5 time slots. Never for 2 or for 4. Why? Because if the master occupies, for example, for 3 time slots, the medium stays on this frequency, sending more bits, that's more energy efficient, while jumping through frequencies, that's not a good idea. So you stay on the frequency, send more data to a single slave. The other slaves will continue to jump through the frequencies, because if you're not the receiver of data, you don't know anything about this communication. So this is why we continue here with fk plus 3 and not with fk plus 1. So all the slaves, they strictly follow the hopping pattern, and only a sending station can remain on a certain frequency. As shown here, after fk with fk plus 1. But the next slot we use fk plus 6. So all the slaves, they continue to hop. Again, that makes the system much simpler. Because otherwise, if a station does not receive the packet, you're out of sync. If you now stay with the frequency, etc., etc. So no, we strictly follow the hopping pattern. That's the basic idea here. Okay, so strict hopping, yeah?
But the idea of hopping was to avoid collisions between different.
The idea of hopping was to avoid the collision between different Bluetooth piconets, and they have complete different hopping patterns.
So they start with an initial random.
The start is always based on the clock, which is not synchronized between the devices if you're not within the same network, completely unsynchronized, plus the MAC address. And the MAC address is unique. So you never have the same hopping patterns, unless you have same MAC address and start at the same point. So that's the idea, and then I will briefly go over this. We again have packet formats, like you see certain payloads, packet headers. If you count the bits, you will see, that's way 3 times larger, the packet header. Why? We simply transmit the bits in the packet header 3 times to make it more robust. So we have a certain forward error correction already in the packet header. We have addresses, one broadcast and 7 slave addresses. And we have a very simple ARQ scheme. We have an alternating bit protocol. Remember back in telematics, alternating bit protocol, yes, that was sequence numbers, just a single bit, indicating the packet. That was not very efficient if you send more data, but here we have a half duplex scheme. We use the time to separate the direction, but we always use master to slave, then slave to master to slave, slave to master. This is why alternating bit is okay, is sufficient for sequence numbering. So you see, it's a very, very simple scheme. So yes, we have packet format, different payload types for audio, payload types for data, different data rates. It's just to give you an idea of the basic Bluetooth. This is where we have this 723.2 kilobit per second maximum. Downstream, for example, and upstream 57. That's good for surfing, browsing, whatever. And then we have symmetric connection oriented with the 64 kilobit per second, and different amount of data of redundancy needed for forward error correction. For voice, there is no acknowledgement, no repeating data in case of errors, etc. We use FEC for voice. That's one of the differences. Okay, what is now again interesting is how you do this communication. Here you see the scheme way different to wireless LAN. And this is why I put more emphasis on this, what we sometimes, quite often ask also in the exams, compare wireless LAN with Bluetooth, because they are really different from the basic design. Here we have a master, and the master is responsible for the network. And for example, the master knows if you set up a voice communication, and then you can have these SEO packets, so this is synchronous, connection-oriented, in fixed distance. So that means periodic sending of data. This gives you certain guaranteed data rates. That's different from wireless LANs. Here you can reserve time slots, periodic single slot packet assignments. And this now then in the end results in a 64 kilobit per second full duplex point-to-point connection. That's exactly what is needed for voice communication. That's what you usually have. If you have a wireless headset and a smartphone, then you can use this. And then you have this variable packet size asymmetric thing where you can, as a master, actually, that's shown here, send something to a slave, and then in the next slot, the slave can answer. So in Bluetooth, it's always that master sends something and directly in the next free slot, the slave can send something back, or the slave can at least acknowledge the correct reception of the packet. So that's shown here, shown here. The master can also use 3 slots, but again, in the next slot, the slave can send back something or at least acknowledge, or the master can allow a slave to send more data, because slave may indicate that they have more data to send. We need more data, a higher data rate. The master can then allow this higher data rate. So that's completely different from wireless LANs, where you have to compete for the medium, contention, slots, etc. There are no slots for contention. There is no contention because there's a master. It's like in a classroom, a teacher and polling the students, no contention at all. So that's the idea. And if you want to send something, you have to wait until the master actually polls you. And then as you have to send something, then you can say no, which at least acknowledges that this polling was received, or you can send data. So different scheme. If something goes wrong, well, in wireless LAN, we have the scheme no acknowledgement. Here, well, it's can be similar. That, for example, if the master sends something to a slave, the condition is the slave receives it. So not an error in the packet header, because if you do not receive your address, you cannot acknowledge because you don't know that this packet is for you. So assuming you received the header, correct header, but there was an error in the payload, then you can immediately give a negative acknowledgement back, and maybe you can also send data. Then sooner or later, maybe directly afterwards, the master can retransmit. It could be also the case that there's an error when the slave sends something to the master, but the master decides, well, first of all, I have to get rid of this packet H. I have to first to communicate to the other slave, which acknowledges the packet. And then maybe later, the master sends back a negative acknowledgement. Negative acknowledgement simply means the wrong sequence number, alternating bit, either 1 or 0, 1, 0, 1, 0, 1, 0. That's the normal pattern we assume. But if there's an error, I send back a 1 while the receiver is expecting a 0. And that indicates, oh, negative acknowledgement. So there is no special negative acknowledgement packet. It's just the simple alternating bit scheme I introduced in telematic. So nothing special. So that's the basic idea here. So it's a kind of a robust system. We separate different networks by this hopping. This is why sometimes this is called a frequency hopping code division multiple access, because we separate networks by code, but we use frequency hopping. We do not spread the signals with a secret code. Something like this could have been used, but this is more complicated. Here you use hopping, which is much simpler. Okay, so quite robust. We have way more states trying to save energy. So usually if you transmit something, you have an address, and if you're connected, you're in the connected mode. And all the active devices, they switch between connected mode, transmitting, connected, transmitting. And then there are some more low power modes where you basically can save a lot of energy. So park mode, sniffing mode, hold modes. Without going into details, that means that you only, for example, periodically listen for your master. So you sleep, you listen periodically. And the period itself is set by the type of traffic you have to send. You can imagine we can send a lot of data by allocating a higher data rate for a short amount of time, or by quite often sending a little bit. So there are different ways of sending data, which directly has an influence on the latency. On average, it's the same data rate, but latency might be different. So waiting for a long time, then sending a huge chunk of data, that's different from sending always some bytes. But then you cannot sleep during that time. So there's a certain trade-off, as we will see. So standby, inquiry, paging, different states. Usually you are connected, you have your active member address, but you can step back a little bit, go into hold or sniff modes. So periodic listening, not in each slot. Yeah? Active member address and parked member address. So active member and parked member. So active members, maximum 7 slaves, 1 master. 3-bit address, parked member address, 8-bit address. That's the difference. There are many, many details, as you can imagine, that would simply be too much. I just want to point out the effects of how we can use the system. Look at, for example, these two schemes here. We want to transmit 38.4 kilobit per second. We can either sniff every 1.28 second or every 40 milliseconds. But you see the result, 4 microamps, 0.5 microamps. Although the average data rate is exactly the same, well, it's a different. And sleep modes, deep sleep, etc., just some microamps compared to milliamps. So, and that was just an example of one of the very early day chips. So yes, depending on the data rate, depending on what you do, you can have pretty different power consumption, which is extremely important if you operate it as a headset, where you say, oh, I want to talk for at least 12 hours, something like this, and have standbys for 1 week. So, and you cannot do this with a wireless LAN device. No way. And even this is not low energy. Today we have Bluetooth low energy, which again is a little bit different. Okay, power consumption is quite different. These were more or less the first then Bluetooth devices. You see Euro here and Cambridge Silicon Radio device there. So it's a USB adapter. Today, that's a very simple chip, very tiny chip integrated everywhere. Additionally, to these lower layers, we have a lot of management protocols. I want to focus again only on one part of it, a little bit of security, but not on all these details. So segmentation, reassembly, quality of service specification. So you can say, I want to have a guaranteed data rate, I want to have a maximum jitter, burst size, etc., etc. So if you're interested in this, that's an internet standard specifying the quality of service. Group specifications and all these. We have many different layers for this. This L2 cap is the layer managing all these different types of, well, data streams with packet formats. One thing I want to point out is that's what you experience using Bluetooth devices, and that's security. Compared to wireless LAN, everyone knew, well, we want to replace a cable. Cables are under your control. Wireless, you don't know. So this is why from the early days there was a lot more security already integrated into Bluetooth compared to wireless LAN. Wireless LAN with WPA, etc., is also a secure system, but it's not integrated from the early days. Here we have a system that basically, if you have two brand new Bluetooth devices, they have never seen each other, you usually have to enter a pin 1 to 16 bytes, sometimes only 4 zeros or whatever, so not very strong. but the devices are open for pairing only under certain conditions, like the cars only when the ignition is on, but the engine is not running. And hopefully no one pairs some other devices to your car during that time, for example. Otherwise the car does not accept other devices. Or only if you push certain buttons with the Bluetooth devices, etc., etc. Then that means two devices, they pair, and after that they generate authentication keys, and they are usually in permanent storage, unless you clear it, and that means the two devices, they know each other. And as soon, so you generate a so-called link key, and as soon as those two devices, they see each other again, they can temporarily generate an encryption key, 128-bit encryption key. So two devices see each other again after 1 week, and then they can generate a new encryption key. Based on this encryption key, they can generate individual payload keys for different data streams. That's a payload stream, and then that's the key used for encryption of the payload. So that's the scheme used in Bluetooth to implement some security, at least some.
Could you sum up again why it's less power intensive than wireless LANs they use?
Well, the encryption scheme and power, etc., not the encryption. The main reason why it's more saving more energy basically is by far not that high range, data rate. And by using this simple scheme, you can basically build simpler hardware. We do not have the complex modulation scheme, so physics is simpler, and you have more elaborated sleep modes compared to wireless LAN, where unless you use this sleep, wake, sleep, whatever things, you do not really put the wireless LAN adapter that much into sleep compared to the Bluetooth. But really compared to wireless LAN, it's in the end, it's not different physics. Well, it's the same nature, but it's lower data rates, by far lower data rates. So, some security built in. We have some more additional protocols like service discovery that's used for discovering of other devices. That's also something quite interesting for everyday use, because you have to find services. Not only MAC addresses, but services. Why? Well, for example, if you want to print something, it's not of big use if you find a headset. Or if you want to type something, you need a keyboard, something like this. So, different features for different devices. So, discovery and then how to use, that's in addition some more protocols. So, discovery of services, service records, etc. And there are just some additional protocols. One more thing I want to point out is that Bluetooth became over the years extremely complicated. Why? Physical layer, data link layer, that seems pretty simple, but the point is, if you want to keep the system simple, then a headset only picks out certain protocols out of many of the protocols. So for example, maybe a headset only needs a small fraction of the protocols. A keyboard maybe needs different protocols. So depending on the usage of the devices, you need different types of protocols, different parameters. Maybe you don't need TCP, maybe you need only IP, maybe you don't need this at all because your audio device, you need only raw baseband services, etc. And so the Bluetooth Alliance came out with so-called profiles. And the profiles shown here in orange, they pick out certain parts of the horizontal protocols together with settings. And this is why we had, for example, cordless telephony profiles, or object push profile, etc., etc., or basic printing profile, hands-free operation. Some profiles were competing, they are not compatible, etc., etc. And this is, by the way, one of the reasons if you have a Bluetooth device, that does not necessarily mean it can talk to another Bluetooth device, because there's no audio output on a keyboard, for example. That's a good reason. But sometimes it's also for strange reasons that your smartphone from a certain manufacturer will not allow the attachment of certain types of other devices. So you cannot use it as a modem, for example, via Bluetooth. So sometimes that's very strange. Sometimes you cannot use your Bluetooth device with all the features in a car, etc., etc. So that is cumbersome. Additionally, we have many Bluetooth versions. So what I explained right now was Bluetooth 1.1. We have new standards, 2005, a Bluetooth standard with higher data rates. We have adaptive frequency hopping, that's something I will explain right now, to avoid interference. We have enhanced data rates, and that was the point when IEEE did stop standardizing Bluetooth, and the Bluetooth Alliance went more and more into higher data rates, and IEEE said, this is why we have wireless LANs. So stop using Bluetooth for higher data rates, this is why we have wireless LANs. And so we have even more using NFC for pairing. And the funny thing is, 2009, Bluetooth suddenly said, oh, we also have high data rates. Why? Bluetooth 3.0 simply integrates wireless LAN. This is why Bluetooth now has higher data rates, which is not Bluetooth anymore, the original Bluetooth, but it's Bluetooth with wireless LAN. 2010 is now the Bluetooth we use today is Bluetooth low energy. And the special feature there is a much, much faster connection setup. This is used, for example, to read out a tag. And that's a competitor for NFC. More wider range, thus we have maybe some more problems with privacy. Compared to NFC, NFC only has some centimeters to read out a tag. BLE, Bluetooth low energy, can be used there for certain tags. This is what Apple uses, for example, for these, for reading out tags, etc. So you see, it's not the Bluetooth we once had as cable replacement, but today it's a very elaborated standard, but it left the IEEE standardization because IEEE said, well, go for wireless LAN if you want to have higher data rates, or go for NFC if you want to have NFC functions. But the industry alliance around Bluetooth wanted to integrate more and more features. So that's the story why today we have Bluetooth with way higher data rates. So now, that's 802.15.1, at least the core. Just to make the picture more confusing or complete, we have .2, that's about coexistence, that's what I will explain just in a minute. We have even higher data rates for low power. We have several more subgroups. It's really confusing, many subgroups, not that much standard. We have quite interesting .4, low rate, very low power. That's used for building automation. That's another standard. If you're interested in this, Zigbee is the alliance for this. So Zigbee uses 15.4, quite similar the relation from the alliance to IEEE, like it was Bluetooth to the IEEE standard. So this is something used for very low power, so 10, 20 years of operation in building automation. Complete, different technology, way lower data rates. No more master controlling, CSMA, CA scheme. It's a different scheme. If you're interested in this, we use this for our sensor networks. So, complete different thing. You see, there are even more standards. So if you're interested in really high data rate, .7, 802.15.7, small networks, ultra high data rate using visible light, body area networks, mesh networking, many extensions, RFID technologies, ultra wideband technologies. If you're interested in this, come to our group. This is what we use for our sensor networks. You see, there's a lot more, but that's going into the details doesn't give you really more understanding of different technologies. Yeah?
You just mentioned NFC, or slides or within slides.
NFC is not mobile communication. I mean, NFC is basically a near-field communication. There are slides here in this chapter, but hidden slides, you covered 1 to 3 centimeters. That's not mobile communication. That's just using a wireless technology. But you will find slides exactly in this chapter about RFID/NFC. NFC is a special standard. It's a part of RFID, radio frequency identification technology. No magic behind that, not at all. You could also use a cable. From a scientific point of view, boring. I mean, there's nothing behind NFC. So, And many more standards not covered here because up to now not successful or already dead. So, last two slides. Now we put everything on the ISM band compared to GSM, UMTS, etc. with the license band. Many things like microwave ovens, like light bulbs using microwave, like microwave welding, whatever. And we will have many interference on the physical layer. Yes, physical layer, that's why we use maybe spread spectrum, but also on the MAC layers. The MAC algorithms are not harmonized between here, this light bulb, and your Bluetooth. Not at all. So you hope there's not that much interference. So on this slide, you see one example, one solution. So if you have wireless LAN, so now these are our 3 bands. One set, for example, oh no, that's different. 13.7.1, 3 bands non-overlapping with diffs, sending data, CIFs, acknowledgement, etc. If we now have Bluetooth, basically Bluetooth jumps exactly into these bands, not coordinated. So what happens if you perform carrier sensing in wireless LAN? Oh, the carrier is busy. I step back, but this is Bluetooth. Bluetooth never respects wireless LAN. So this is a problem, or it can be a problem. So there are publications telling a complete breakdown of wireless LAN to almost no effect. But now there's a solution, and this is integrated into Bluetooth. It's adaptive frequency hopping. So if your device uses a certain channel, Bluetooth avoids this channel. But if you use all the channels in your environment, what to avoid? But at least on a single device, Bluetooth avoids the wireless LAN channels you use. So always the good advice is go to 5 gigahertz because there's no Bluetooth. So that's one way of avoiding interference on layer 2. Okay, that's all. That's all for wireless LAN, all for these unlicensed systems. We have 2 more lectures, one for layer 3 and one for layer 5, layer 4, and a little bit of Outlook because there's not that much on layer 3 and layer 4. And then we have the exam on the last lecture, no lecture but exam. So that's basically all. So you should be able, with the help of this chapter, to compare this local area, personal area technology when it comes to medium access, to pros, to cons, to complexity, to offer services. That's a typical thing. So what can you do with it? No one asks you for packet formats, but you should be able to explain medium access between these two for these technologies. The problems, as you see here, you can imagine if it's uncoordinated medium access, uncoordinated physical layers, you will run into some problems. Okay, so that's basically all for layer 2. And next time I will explain some mobility technology when it comes to IP, the internet layer. Thanks a lot for today.